Beneath the shimmering surface of our oceans lies a world more mysterious than the cosmos above. A realm where bizarre phenomena occur without explanation, where vessels disappear without warning, and where ancient structures challenge everything we thought we knew about human history. From the eerie underwater lights that sailors have reported for centuries, to massive unexplained sounds that echo through the deepest trenches, to massive rogue waves that appear from nowhere and vanish just as quickly. These aren't tales from science fiction. They're documented events that continue to baffle scientists and explorers alike. The ocean, covering more than 70% of our planet, remains largely unexplored, hiding secrets we've yet to comprehend. So dim the lights, settle in, and join me as we plunge into the most perplexing maritime mysteries ever recorded. The deeper we dive, the more inexplicable it becomes. Let's get started. Our story starts with the eerie, silent drift of a vessel that seemed to have been abandoned by time itself. The MV Joyita, a once proud merchant ship built in the early decades of the 20th century, was discovered adrift in the vast expanse of the South Pacific, its decks quiet, its cabins empty, and its fate shrouded in mystery. On a cool November day in 1955, a passing vessel came upon an unsettling sight, the MV Joyita, bobbing listlessly in the blue Pacific waters near the Solomon Islands. At first glance, there was nothing remarkable about her silhouette against the endless horizon. Yet, as observers drew nearer, the unsettling truth became apparent. The ship was deserted. No lively chatter of the crew echoed on deck. No figures could be seen moving about the cabins or on the bridge. Instead, there was only the sound of the wind, the soft lapping of waves against the hull, and the silent testimony of an abandoned life at sea. Constructed in the 1920s, Joyita was designed for steady voyages between islands and ports, carrying goods and sometimes passengers over vast distances. By the time she was found, she was already an aged ship, having weathered countless storms and journeys. Yet, despite her apparent wear, she had not sunk or broken apart. Instead, she drifted intact, her hull largely preserved, and her cargo seemingly undisturbed. What made the case all the more puzzling was that the vessel's lifeboat was missing, and her navigational instruments, though weathered, appeared to suggest a course that could not be easily explained. Investigators later discovered that the ship had been carrying supplies and cargo, with provisions that indicated a journey planned for several more days. Her logbook, recovered from a secure compartment, revealed that the last entry had been made without any sign of distress or emergency. There was no frantic notation, no desperate plea for help. In fact, the entry was calm and unassuming, as though nothing out of the ordinary had occurred. This discrepancy between the normalcy of the final log entry and the total absence of her crew deepened the mystery, leaving maritime experts and historians to puzzle over what could have prompted such a sudden abandonment. Among the many theories proposed, one suggests that a catastrophic event may have struck unexpectedly. Perhaps a rapid flooding in one or more compartments made the vessel unstable, forcing the crew to take to the lifeboat in haste. Yet, evidence of severe damage or explosive disintegration was never found. Instead, the ship retained a strangely pristine condition, with water present in only some areas of the engine room and cargo holds. The possibility of structural failure or capsizing was considered, but no definitive clues, no broken masts, no shattered equipment pointed toward a violent end. Other investigators have speculated that a mutiny or internal conflict could have led to the crew's disappearance. In the tense isolation of long voyages, disagreements and desperation sometimes simmer beneath the surface. Could the crew have turned on one another, leading to a situation where the survivors, gripped by fear or remorse, chose to abandon the ship? Yet, no signs of violence, no bloodstains, and no evidence of a struggle were found on board. The orderly arrangement of the cargo, the intact state of the cabins, and the undisturbed personal belongings of the crew seem to contradict any notion of a chaotic mutiny or violent uprising. Some have even entertained the idea that piracy might have played a role. The South Pacific has long been a region of turbulent waters, where the shadow of piracy sometimes looms. A pirate attack could conceivably force a crew to abandon ship in terror. But in the case of the Joyita, there were no signs of a breach in the hull large enough to suggest an external attack. No traces of valuables or plundered goods were found missing from the ship's manifest, and the vessel's log did not record any confrontation or distress call that would indicate a violent encounter. Then there is the theory of insurance fraud, a notion that some have found disturbingly plausible. In this scenario, the ship's owners or a group of conspirators might have deliberately staged an abandonment to collect insurance money. They could have engineered a situation where the vessel was left to drift, deliberately removing or concealing critical equipment such as the lifeboat. The calm, unremarkable nature of the last log entry might then have been part of a meticulously planned ruse. However, thorough investigations revealed no conclusive evidence linking the Joyita to fraudulent activities, leaving this possibility as intriguing as it was unproven. As we continue to delve into the facts, another detail adds to the somnolent atmosphere of uncertainty: the state of the ship's cargo. Despite the prolonged drift, many of the supplies remained in place, and the perishable goods, such as foodstuffs and beverages, showed no obvious signs of spoilage that would be expected after a lengthy period adrift in warm waters. This observation suggests that the ship may have been abandoned relatively quickly, or that environmental conditions somehow preserved the cargo. The exact timeline of events remains a subject of debate among researchers, each hypothesis adding another layer to the quiet mystery. Adding to the perplexity is the question of navigation. The instruments on board, though outdated, seem to suggest that Joyita had maintained a course that was neither erratic nor influenced by external forces such as strong currents or winds. How, then, did the ship come to be found so far from its intended route? Did the crew set out in the lifeboat and vanish into the darkness of the Pacific, or was there another, more inexplicable force at work that altered the ship's course without the crew's intervention? These questions, like soft whispers in the night, remain unanswered, contributing to the enduring allure of the case. Over the decades, the Joyita enigma has inspired countless theories, research papers, and even works of fiction. Maritime enthusiasts pore over every detail, every faded note in the log, every dent in the hull, every inexplicable gap in the vessel's inventory, in search of clues. Some researchers have revisited the site where the ship was found, hoping that advances in underwater imaging and oceanographic technology might shed new light on the circumstances of her abandonment. Others have re-examined the archived records and testimonies of those who once sailed these mysterious waters, looking for inconsistencies or hidden messages in the official reports. Yet, as the years have passed, the Joyita remains as enigmatic as ever, a ghostly relic of a bygone era whose final moments continue to elude definitive explanation. The silence of the empty decks, the unanswered questions in the logbook, and the calm appearance of a vessel left to drift against the endless blue of the ocean create a scene that is both haunting and mesmerizing. It is a reminder of the vastness of the sea and the limitations of our understanding, a quiet mystery that invites us to pause, reflect, and perhaps even drift off to sleep, lulled by the gentle, rhythmic sound of waves against an abandoned hull. In the broader context of maritime history, the case of the MV Joyita is not an isolated anomaly. The oceans have always been a repository of secrets, holding within their depths stories of adventure, tragedy, and inexplicable events. The Joyita is one among many vessels whose fates have become tangled in the mysterious interplay of human error, natural forces, and the relentless passage of time. And yet, its story stands out for the peculiar calm that surrounds its abandonment, a calm that is both unsettling and strangely beautiful in its quiet finality. For those who find solace in the gentle unfolding of a mystery, the Joyita offers a narrative rich with unanswered questions and subtle hints of a dramatic past. The ship's condition, the nature of her cargo, and the baffling absence of her crew combine to form a tapestry of facts and conjecture that has resisted easy explanation. Every detail, from the missing lifeboat to the undisturbed state of the supplies, serves as a gentle puzzle piece, inviting us to consider the many ways in which human lives can be upended by the unpredictable forces of nature and circumstance. Hala Holo began its life as a pleasure craft built between 1959 and 1961 by E.R. Simmerer. Launched in 1963 for Arthur F. Stubenberg, the ship was originally designed for leisurely voyages along the coast, meant for relaxation and gentle adventures on the open water. However, its destiny would take a dramatic turn when, on the 15th of September, 1978, Stubenberg sold the vessel to John Laney for $75,000, a sum paid in installments, and the ship was then converted into a research vessel. Later that year, in October, the Research Corporation of the University of Hawaii chartered Hala Holo for their ambitious ocean thermal energy conversion project. With this new role, the vessel was expected to brave the deep, mysterious Pacific, carrying scientific instruments and a crew dedicated to unlocking the secrets of renewable energy from the ocean's thermal gradients. On the 9th of December 1978, Holo departed from Honolulu bound for Kauai. The journey, anticipated to last until the 11th, began without incident. Yet by the following day, the vessel had seemingly evaporated. No distress calls were heard over the radio, no lifeboats were launched, no debris field marred the otherwise pristine blue expanse. Instead, the ship had simply disappeared, a silent, unaccounted absence in a vast, unpredictable ocean. Investigators soon discovered that the weather on the day of the disappearance was far from benign. Forecasts and reports indicated that swells were exceptionally high, ranging from 14 to 17.5 feet. In such tumultuous conditions, even a sturdy vessel could be pushed to its limits. The MV Holo, with its aged hull and repurposed design, was especially vulnerable to the wrath of the sea on such a day. One of the most compelling and chilling pieces of evidence in this mystery came from the vessel's own modifications. To facilitate the Ocean Thermal Energy Conversion project, alterations had been made to the ship, including the removal of a 2x4-foot hatch door from the steering room on the fantail. This hatch, originally an integral part of the vessel's design, provided a protective barrier against the relentless force of the sea. Its removal, intended to allow piping to lead into the engine room for a hydraulic winch, left an unsealed opening. Rather than being securely replaced, the opening was hastily covered with a sheet of plywood. In calm conditions, such an improvisation might have been tolerable. However, on a day when the ocean was churning with swells far exceeding 6 feet, the threshold at which the Coast Guard warned of potential water ingress, the inadequately covered hatch became a critical vulnerability. Experts from the Coast Guard's Marine Casualty Investigation Team later scrutinized the available evidence. They theorized that the absence of any debris field or distress signal indicated an immediate and catastrophic loss of stability. In such a scenario, water could have poured into the lower decks almost instantly through the unsealed hatch, destabilizing the vessel in a matter of moments. The flooding may have begun as a slow trickle that undermined the ship's balance, only to reach a tipping point and cause Holo to capsize abruptly. Without time for the crew to launch life rafts or send out distress calls, the entire vessel was swallowed by the unforgiving ocean. Some investigators have considered an alternative possibility involving the vessel's anchors. In heavy seas, unsecured anchors can become dangerous projectiles. It is speculated that loose anchors might have collided with, or even breached, the transom, the rear part of the vessel, thereby causing additional water ingress. Whether it was the unsealed hatch, the shifting anchors, or a combination of both, the outcome was the same. Holo was overwhelmed by the ocean's power and disappeared into its depths. A year after the disappearance, on the 9th of December, 1979, the National Oceanic and Atmospheric Administration research vessel Townsend Cromwell picked up faint signals emanating from the seafloor. These signals, detected by sensitive instruments, appeared to originate from Holo. However, rather than a concentrated wreckage, the instruments found the signals scattered, located between 200 and 500 meters apart from one another. This scattering suggested that the ship had not broken apart gradually, but had met with a sudden and violent demise. The official resting place of MV Holo was marked at 20 degrees 6 minutes north and 156 degrees 28 minutes west, yet no definitive wreckage has ever been recovered to date. Over the ensuing decades, as researchers revisited the evidence, the mystery of Holo has only deepened. Shipbuilders and marine engineers have meticulously analyzed the vessel's design modifications, while oceanographers have studied the harsh, unforgiving conditions of that December day. The interplay between human error, exemplified by the hasty modification and unsecured hatch, and the raw, untamed forces of nature remains at the heart of the investigation. It is important to note that the disappearance of Holo is not an isolated event in maritime history. The ocean, vast and enigmatic, has claimed many vessels over the centuries under mysterious circumstances. Yet what sets Holo apart is the eerie lack of any warning signals or debris, and the fact that the vessel was laden with valuable scientific instruments meant to advance our understanding of ocean thermal energy conversion. In a sense, the mystery is amplified by the ship's dual identity, once a vessel built for leisurely voyages and later a research ship tasked with a mission of scientific inquiry. This transformation, from an emblem of recreation to a beacon of scientific progress, adds a poignant layer to the unfolding tragedy. In the years following the disappearance, numerous theories have emerged. Some researchers suggest that human error played a larger role than initially assumed. Perhaps the decision to remove the hatch door and cover it inadequately was a critical oversight that was overlooked in the rush to adapt the vessel for the ocean thermal energy conversion project. Others have speculated that a sudden, unforeseen natural event, a rogue wave, or an unexpected shift in ocean currents might have interacted with the vessel's vulnerabilities to cause its rapid sinking. Despite the many investigations and hypotheses, there is still no universally accepted explanation for what truly happened to the MV Holo. The mystery lingers like a quiet echo beneath the waves, a reminder that even in this modern age of advanced technology and stringent safety protocols, the ocean remains an unpredictable and often inscrutable force. The disappearance of Holo has been carefully documented in marine casualty reports and has become a case study in the challenges of maritime safety, vessel design, and the role of human factors in hazardous conditions. For those who have spent long, quiet hours on the water or have gazed upon the endless horizon, the story of MV Holo is both a cautionary tale and a source of somber fascination. It speaks to the inherent risks of the sea, where a single oversight or moment of miscalculation can lead to irreversible consequences. And while the investigation may have narrowed the possibilities down to a few likely scenarios, the full truth remains just out of reach, a puzzle waiting to be solved by future generations of marine researchers. Even now, as technology continues to improve and our ability to probe the depths of the ocean advances, the fate of Holo still serves as a humbling reminder of our limitations. Remotely operated vehicles, sophisticated sonar mapping, and high-resolution imaging have all been employed in the search for answers. Yet the scattered signals on the seafloor, the absence of coherent wreckage, and the lingering questions about the ship's design modifications continue to defy easy explanation. Imagine, as you listen to these words in the quiet moments before sleep, the silent, rolling waves and the cool mist of ocean spray. Picture the vast, unending blue and the deep mystery of a vessel that once carried dreams of scientific progress. The story of MV Holo is one that resonates with the timeless power of the sea, a force that can nurture, sustain, and, in moments of tragedy, claim what we hold dear. Vast stretches of the ocean, under the quiet veil of night, sometimes reveal a mysterious and almost surreal glow, a milky, luminous haze that spreads across the dark waters like a gentle blanket. This phenomenon, known as the Milky Sea, has been reported by sailors for centuries and more recently confirmed by satellite observations. Although documented for hundreds of years, its underlying cause remains a subject of scientific debate, a mystery that continues to intrigue oceanographers and marine biologists alike. Historical accounts of the Milky Sea describe a scene of calm wonder. In earlier centuries, seafarers recounted nights when the normally inky black ocean suddenly transformed into a vast, glowing expanse. These accounts, written in logbooks and passed down through maritime folklore, spoke of an eerie, milky radiance that could be seen even from the decks of ships, sometimes extending for miles across the water. With the advent of satellite technology in the latter part of the 20th century, researchers were able to confirm that such events are not mere figments of imagination but real, observable occurrences. Satellite imagery has captured these white, luminous patches spanning hundreds of square kilometers in remote regions of the world's oceans. The most widely accepted explanation involves bioluminescence, a natural light produced by living organisms. In the case of the Milky Sea, many scientists propose that bioluminescent bacteria are responsible. Under the right environmental conditions, these bacteria can multiply in vast numbers and emit a continuous glow. This process is thought to be triggered by a mechanism known as quorum sensing, whereby the bacteria produce light only when their population density reaches a critical threshold. When conditions are optimal, typically in warm, calm waters with a plentiful supply of nutrients, the bacteria synchronize their light emission, transforming a seemingly ordinary stretch of ocean into a glowing, Milky Sea. One of the intriguing aspects of the Milky Sea phenomenon is its scale and uniformity. Unlike the intermittent flashes produced by individual bioluminescent organisms, such as dinoflagellates, the glow of a Milky Sea is continuous and uniform. It bathes a large area in a soft, steady light rather than a series of twinkling or strobing bursts. This consistency suggests that the phenomenon is not simply the sum of countless individual organisms acting independently, but rather the result of a coordinated, large-scale biological process. The possibility that a single species of bioluminescent bacteria might be orchestrating this light show through chemical communication is a topic that continues to be explored in marine research laboratories. The precise environmental triggers that lead to a Milky Sea event are still not fully understood. Researchers have noted that such events are rare, occurring under specific conditions that have yet to be completely defined. Some studies suggest that regions with stable, warm surface waters and minimal turbulence may provide an ideal setting for the bacteria to accumulate and reach the necessary density for quorum sensing to take effect. Additionally, the availability of organic nutrients, perhaps delivered by upwelling currents or decaying marine life, might further stimulate bacterial growth. The delicate interplay between temperature, nutrient availability, water chemistry, and even local weather patterns creates a unique set of circumstances under which the Milky Sea can occur. Field studies have attempted to correlate satellite observations with in situ measurements. In one notable instance, a Milky Sea event was observed off the coast of Somalia, where satellite data revealed a vast white patch that persisted for several hours. Follow-up expeditions to the region, though challenging due to its remoteness and the unpredictable nature of the phenomenon, have collected water samples and attempted to identify the organisms responsible. While the evidence strongly suggests the involvement of bioluminescent bacteria, no single species has been definitively pinpointed as the culprit. Some scientists speculate that it might be a consortium of multiple species, each contributing to the overall luminescence in a subtle, synergistic manner. Another hypothesis that has been considered is the role of phytoplankton. Certain species of phytoplankton are known to exhibit bioluminescence, and large blooms can sometimes cover extensive areas. However, the bioluminescence produced by phytoplankton tends to be more sporadic, with a flickering quality rather than the steady glow characteristic of Milky Sea events. Moreover, phytoplankton blooms are often associated with other observable factors, such as changes in water color or increased levels of chlorophyll, which are not always present when a Milky Sea is reported. Thus, while phytoplankton might contribute in some instances, the evidence seems to lean more heavily toward bioluminescent bacteria as the primary cause. The phenomenon also raises interesting questions about the behavior and ecology of the organisms involved. For bacteria to emit a continuous glow over an extended area, there must be not only a high population density, but also a uniform distribution throughout the water column. This suggests that the bacteria might be transported or aggregated by ocean currents, or perhaps that they are more prevalent in certain layers of the water due to variations in oxygen levels, temperature, or salinity. These physical factors can create stratified layers in the ocean, where microorganisms thrive in niches that offer the perfect balance of conditions. The Milky Sea might then represent a surface manifestation of these deeper ecological processes, a visible indicator of an otherwise invisible underwater ecosystem at work. While the bioluminescent explanation is compelling, the Milky Sea phenomenon still holds a certain allure for those who ponder alternative possibilities. Some early theories propose that the glow could be the result of chemical reactions involving minerals, or even the reflection of moonlight off of unusual cloud formations in the atmosphere. However, these ideas have largely been set aside in favor of biological explanations, particularly as modern instruments have confirmed the presence of bioluminescent organisms in the affected waters. Nonetheless, the mystery endures in the sense that the full chain of events, from the initial bacterial proliferation to the conditions that trigger their synchronized light emission, remains only partially unraveled. Scientists continue to study the Milky Sea through a combination of remote sensing, direct sampling, and laboratory experiments. Advances in satellite technology now allow for the detection of these luminous events with greater precision than ever before, while autonomous underwater vehicles, AUVs, provide an opportunity to sample and monitor remote areas where Milky Sea events occur. Laboratory studies, on the other hand, are beginning to shed light on the molecular mechanisms behind bacterial bioluminescence, offering clues about how these tiny organisms might coordinate their activity over such vast distances. Together, these approaches are gradually piecing together a more complete picture of one of nature's most enigmatic light shows. The calm, steady glow of a Milky Sea is a reminder of the quiet power of nature, a natural event that occurs far from the hustle and bustle of human civilization. There is something deeply soothing about the idea of the ocean, normally dark and mysterious, suddenly bathed in a gentle, milky light. This glow, spreading silently across the water, invites a sense of wonder and tranquility. It is a phenomenon that, despite its rarity, has the potential to captivate anyone who has ever gazed out over the sea at night. Even as researchers work diligently to understand every nuance of the Milky Sea phenomenon, there remains an intrinsic magic in the way the ocean can transform before our very eyes. It serves as a gentle reminder that, despite our many advances in technology and science, the natural world still holds secrets that elude full explanation. The Milky Sea is a moment of beauty in the vast darkness, a transient luminous display that connects us to the fundamental processes of life in the ocean. In the quiet aftermath of such an event, one can almost imagine the myriad tiny organisms, each playing its part in a grand, coordinated dance of light. Their glow is not the result of conscious design, but the outcome of evolutionary processes honed over millions of years. In this light, the Milky Sea is both an expression of life's persistence and a celebration of the natural order, a phenomenon where biology, chemistry, and physics converge in a delicate, ephemeral spectacle. The story of the Milky Sea is also one of human curiosity and scientific endeavor. For centuries, seafarers relied on their observations of the sea to navigate and understand their world. Now, with the aid of satellites and sophisticated underwater sensors, we are able to observe these ancient phenomena in ways that our predecessors could only dream of. Every new Milky Sea event captured on camera or detected from space adds a small piece to the puzzle, gradually transforming myth into measurable data, folklore into studied fact. As researchers continue to gather data and refine their models, the hope is that the full story of the Milky Sea will eventually be told, a narrative that explains not only how such vast expanses of glowing water come to be, but also what they can tell us about the state of our oceans. This research has broader implications too. Understanding the conditions that lead to large-scale bioluminescence can help in monitoring ocean health, studying climate change, and even in detecting other natural phenomena that might be hidden in the dark depths of the sea. In moments of quiet reflection, it is comforting to know that the natural world, in all its complexity and mystery, continues to reveal itself in unexpected ways. The Milky Sea, with its ghostly luminescence and tranquil beauty, is a testament to the enduring wonder of nature. Its gentle glow invites us to slow down, to listen to the soft sounds of the ocean, and to marvel at the processes that occur far below the surface, a serene, scientific lullaby that soothes the mind and kindles the imagination. The bloop is an enigmatic, ultra-low frequency sound that was recorded in 1997 by a network of hydrophones deployed by the National Oceanic and Atmospheric Administration. It is a sound of immense power that traveled thousands of kilometers through the deep ocean, its origin remaining a topic of debate and fascination for scientists and enthusiasts alike. The sound was characterized by a rapid rise in frequency over the course of about 1 minute, with an amplitude so high that it was detectable by sensors located over 5,000 kilometers away. Initially, the unique profile of the sound ignited wild speculations. Some even suggested that it could be produced by a giant, unknown marine creature of unprecedented size. This hypothesis was fueled by the fact that, at the time, no known animal was capable of generating a sound with such low frequencies and such extraordinary energy. However, as researchers scrutinized the waveform and acoustic signature of the bloop, many began to favor a natural explanation. Detailed spectral analysis revealed that the characteristics of the sound closely matched those produced by large-scale icequake events. In these events, massive sheets of ice, such as those found in polar regions, fracture or calve from glaciers or ice shelves. When such fracturing occurs, it releases a burst of energy that propagates through the water as sound waves. The resulting acoustic signal exhibits an upward sweep in frequency as the energy dissipates, a profile that is remarkably similar to that of the bloop. Deep investigations into the sound's properties have compared it to other natural acoustic phenomena observed in the polar regions. Icequakes, for example, are generated when stresses build up in large ice formations, and the sudden release of that energy produces sound waves that travel great distances in the ocean. The way the bloop's frequency increased gradually over time is consistent with what scientists would expect from an ice calving event. As a massive iceberg breaks away from a glacier, the complex interplay between the fracturing ice, water pressure, and the surrounding cold water creates a sound that is both powerful and distinctive. Despite the strong evidence supporting the icequake hypothesis, not every detail of the bloop has been fully explained. The exact location of the sound's origin remains somewhat ambiguous, though it is believed to have been recorded in a remote region of the South Pacific. The ocean is an environment of extremes and mysteries, and even with modern technology, pinpointing the precise source of such sounds can be challenging. Factors like sound refraction in water, the variable temperature and salinity gradients, and the immense distances involved all complicate the matter. What makes the bloop particularly fascinating is not just its singular nature, but also the broader implications it has for our understanding of the deep ocean. The deep sea is one of the least explored frontiers on Earth. More than 95% of our oceans remain unmapped and unobserved, and countless natural phenomena await explanation. The bloop serves as a gentle reminder that our planet's underwater realm holds secrets that can challenge our assumptions about the natural world. Acoustic signals like the bloop also help researchers refine their methods for studying the ocean's deep interior. By comparing recordings from various hydrophone arrays and analyzing how sound waves propagate through the water, scientists gain valuable insights into the physical properties of the ocean. The way sound travels in water is affected by temperature, salinity, and pressure, all factors that vary dramatically with depth. In the case of the bloop, these environmental parameters help to shape the sound's profile, offering clues about the conditions at its source. This, in turn, assists researchers in developing more accurate models of underwater acoustics and geophysical processes. It is interesting to note that when the bloop was first detected, the possibility of an unknown colossal sea creature captured the public imagination. For a brief period, headlines speculated wildly about a mysterious ocean monster that could be responsible for generating such a powerful sound. In many ways, this reflects the human tendency to look for the extraordinary in the unknown. The idea of a gigantic, hidden beast lurking in the uncharted depths of the ocean is undeniably alluring. Yet, with careful scientific analysis and methodical research, the more plausible explanation, one that involves the immense natural forces of the polar ice, gained the upper hand. The scientific community now generally agrees that the bloop is most consistent with the sounds produced by large ice fracturing events. Such cryoseismic activity, where the ice undergoes rapid mechanical failure, produces sound patterns that align closely with the recorded data. The frequency and amplitude of the bloop are within the range that would be expected from an ice calving event, especially when one considers the scale of the ice involved in the polar regions. When a massive ice shelf or glacier undergoes a sudden fracture, it releases an enormous amount of energy. This energy, transmitted as sound through the water, can be picked up by hydrophones that are designed to monitor deep ocean acoustics for geological activity, as well as for monitoring marine mammal populations and submarine movements. Even though the icequake hypothesis is compelling, some aspects of the sound still invite further investigation. For instance, while the overall acoustic signature matches that of an ice calving event, there are subtle variations in the sound structure that some researchers believe could indicate additional processes at work. These variations might be the result of complex interactions between multiple ice fractures, or perhaps they reflect the influence of local oceanographic conditions. The interplay between these factors makes the bloop not just a singular event, but a phenomenon that encapsulates a host of natural processes working in concert beneath the ocean's surface. The recording of the bloop also underscores the importance of long-term monitoring in the field of oceanography. Continuous acoustic monitoring has revealed that the deep ocean is a dynamic environment filled with both expected and unexpected sounds. Over the years, many such sounds have been cataloged, each with its own set of characteristics and potential explanations. In this context, the bloop is one among many, yet it stands out due to its extraordinary amplitude and the wide range over which it was detected. By studying such sounds, scientists can better understand the range of natural phenomena that occur in the deep ocean, from tectonic activity to ice movements, and even the biological sounds produced by marine life. It is also worth considering the role of technological advancements in shaping our understanding of such phenomena. When the bloop was first recorded, the available technology allowed for the detection of sounds over vast distances, but with limited resolution in terms of pinpointing their exact origin. Since then, improvements in sensor technology, data processing, and modeling have greatly enhanced our ability to analyze and interpret these acoustic signals. Modern hydrophone arrays, combined with sophisticated computer simulations, have allowed researchers to create detailed maps of the sound's propagation through the ocean. These maps provide not only clues about the source of the sound, but also insights into the complex dynamics of the underwater environment. The bloop, in its relaxed, almost hypnotic progression of sound, invites us to reflect on the immense power of natural forces. Imagine the slow, almost imperceptible buildup of tension in a massive ice shelf, the gradual accumulation of stress over years or even decades, until finally that tension is released in a sudden, violent fracture. The sound of that release, magnified by the cold, deep water of the ocean, creates a signal that is both awe-inspiring and humbling. It is a reminder of the relentless, unyielding forces that shape our planet, forces that operate on scales and in environments that are far removed from our everyday experience. As the sound of the bloop continues to echo in the annals of oceanic mysteries, it remains a symbol of the unknown. Even with the prevailing icequake explanation, there is a lingering sense of wonder that comes with encountering a phenomenon that defies simple explanation. The deep ocean is a place of perpetual discovery, where every sound, every creak of shifting ice, and every ripple on the seafloor tells a story of a world that is as ancient as it is mysterious. The bloop is a testament to the interplay between technology and nature. It is through the patient work of scientists and engineers, using tools designed to capture the faintest whispers of the deep, that we are able to piece together the story behind such phenomena. The data recorded from the bloop not only enriches our understanding of cryoseismic activity, but also contributes to broader efforts in mapping the dynamics of the ocean. In this way, the mystery of the bloop is not an isolated puzzle. It is part of a larger tapestry of research that seeks to uncover the secrets of the deep ocean. In quiet moments of contemplation, one can almost imagine the distant, icy landscapes that gave birth to the bloop. Far in the polar regions, where temperatures plummet and glaciers dominate the landscape, the slow, methodical processes of nature operate with a precision that is both relentless and serene. The fractures in the ice, the shifting of colossal ice masses, and the gentle hum of the ocean all combine to create a symphony of natural sounds. The bloop is one note in that symphony, a note that carries with it the deep, cold echo of Earth's ancient forces. The deep ocean is a realm of subtle motion, where currents flow imperceptibly beneath the surface in patterns that have long puzzled scientists. These so-called invisible currents are not the visible surface streams driven by wind. They are the quiet, slow-moving flows that shape the ocean's interior over millennia. Unlike the churning waves or the swift surface currents, these deep ocean movements are hidden from the naked eye, operating on density differences created by variations in temperature and salinity, a process known as thermohaline circulation. In the vast darkness of the deep sea, the water is stratified into layers. The cold, dense water of the abyss interacts with slightly warmer layers above it, creating subtle gradients that drive slow but persistent currents. These invisible currents play a crucial role in transporting heat, nutrients, and carbon throughout the ocean, influencing global climate and marine ecosystems. Yet despite their importance, their exact behavior remains a conundrum. One of the key drivers of these currents is the difference in water density. At great depths, even small variations in temperature, by a few tenths of a degree, and differences in salinity can produce significant changes in density. This density contrast sets up a slow, steady flow as water moves from regions of higher density to regions of lower density. Over time, these flows create a global conveyor belt that redistributes heat from the equator to the poles and brings nutrient-rich deep water to the surface in some regions. However, because these processes occur over long timescales and at speeds often measured in mere centimeters per second, they remain virtually invisible to conventional observation. Scientists use a range of instruments to detect and measure these deep ocean currents. Autonomous underwater vehicles, AUVs, equipped with acoustic Doppler current profilers, ADCPs, can measure the speed and direction of water movement across different depths. These ADCPs work by emitting sound waves and measuring the Doppler shift of the echoes that bounce back from particles in the water. By doing so, researchers can map out the invisible streams that thread their way through the deep ocean. Additionally, moored current meters placed on the seafloor provide continuous data, revealing how these currents change over days, months, or even years. Internal waves, subsurface oscillations within the ocean's density layers, also contribute to the complexity of these invisible currents. Unlike surface waves that are visible as ripples on the ocean, internal waves propagate along the interfaces between layers of different densities. These waves can have amplitudes of tens to hundreds of meters, moving vast quantities of water in slow, rhythmic pulses. Their energy is derived from tidal forces and wind, and they play a role in mixing the water column, redistributing heat and nutrients. Although internal waves are not visible on the surface, they can be detected using specialized acoustic and satellite techniques, revealing a hidden world of movement beneath the calm ocean exterior. Another factor complicating the picture is the influence of seafloor topography. The deep ocean floor is not a flat, featureless expanse, but a rugged landscape of ridges, valleys, and seamounts. As deep ocean currents encounter these obstacles, they are deflected, accelerated, or slowed down, creating localized eddies and gyres. These interactions can lead to the formation of boundary layers, thin zones of enhanced mixing near the seafloor, which may in turn generate weak, localized currents that add to the overall complexity of the deep ocean circulation. Even small-scale features on the seafloor, such as sediment waves or buried boulders, can have an outsized effect on the flow patterns above them. One intriguing observation is that these invisible currents sometimes exhibit periodic fluctuations or pulsations. Long-term measurements have shown that even in the deep ocean, currents are not entirely steady. They can vary in strength and direction, sometimes in response to remote events, such as changes in the atmospheric pressure or seismic activity. In some regions, researchers have recorded slow pulses in the deep ocean flow that appear to be synchronized with the tides. These tidal influences, though diminished at great depths, still have a measurable impact on the movement of water in the abyssal plains. The periodic nature of these pulses provides valuable clues about the underlying mechanisms driving the deep ocean circulation. Laboratory experiments have helped to illuminate some of the principles behind these invisible currents. By simulating the conditions of the deep ocean in large, pressurized tanks, scientists can reproduce the stratification and mixing processes that occur naturally. These controlled experiments confirm that when water with different temperatures and salinities is layered, the resulting density gradients lead to slow, diffusive flows. Moreover, they demonstrate how internal waves can be generated and how these waves contribute to the mixing of the layers. Although the scale of laboratory experiments is much smaller than the vastness of the ocean, the fundamental physics remains the same, offering important insights into the behavior of these hidden flows. In situ measurements have also been enhanced by advances in remote sensing technology. Satellites can indirectly detect changes in the ocean's surface temperature and color that hint at the presence of underlying currents. While satellite imagery cannot directly observe deep ocean flows, variations in the surface, such as subtle differences in sea surface height, can be correlated with the movements of deep water. Combined with the data from AUVs and moored instruments, these satellite observations help build a more complete picture of the global ocean circulation, including the contributions of invisible deep currents. Despite these technological advances, many aspects of the invisible currents conundrum remain elusive. The deep ocean is a dynamic and complex system where multiple processes overlap and interact in ways that are still not fully understood. For instance, the interaction between internal waves and seafloor topography can lead to localized zones of intense turbulence, but the precise dynamics of these interactions are still being modeled and debated. Similarly, while the role of density-driven flows is well established, the impact of other factors, such as the release of gas from decomposing sediments or the influence of deep ocean microorganisms, remains an active area of research. One of the challenges in studying these currents is their inherently slow speed and subtle nature. In contrast to surface currents that can be swift and turbulent, deep ocean currents often move at speeds that are difficult to detect without long-term monitoring. This slow movement means that significant changes in the deep ocean circulation may only become apparent over the course of months or years. As a result, researchers must rely on continuous, long-term datasets to identify trends and anomalies. These datasets, though invaluable, also require sophisticated statistical analysis to extract meaningful patterns from the background noise. The implications of understanding invisible deep ocean currents extend far beyond pure scientific curiosity. These currents are a fundamental component of the global climate system. The deep ocean acts as a massive reservoir of heat and carbon, and the slow circulation of these waters plays a critical role in regulating the Earth's climate over geological timescales. Disruptions or changes in the deep ocean circulation could have significant effects on global climate patterns, potentially influencing everything from sea level to weather extremes. Thus, Unraveling the mysteries of these hidden flows is not only important for our understanding of the ocean, but it is also essential for predicting future climate scenarios. Moreover, these currents have practical implications for marine ecosystems. The deep ocean is home to a diverse array of organisms that have adapted to a life of darkness and low energy availability. The movement of water in the deep ocean affects the distribution of nutrients and oxygen, thereby influencing the structure and function of these unique communities. For example, areas with enhanced mixing due to invisible currents may support higher concentrations of life, providing localized hotspots of biodiversity. Conversely, regions where deep ocean flow is minimal might experience nutrient depletion, leading to lower biological productivity. By studying these currents, scientists hope to better understand the delicate balance that sustains life in one of Earth's most extreme environments. Recent field expeditions have continued to push the boundaries of our knowledge in this area. Teams using state-of-the-art AUVs have mapped large sections of the abyssal plains, revealing unexpected patterns in deep ocean circulation. In some regions, the data suggests that invisible currents are more variable than previously thought, with transient pulses and localized eddies that challenge conventional models. These findings underscore the need for more extensive and continuous monitoring of the deep ocean, particularly in the Hadal Zone, where conditions are the most extreme and our current understanding remains limited. Advanced computational models are now being developed to simulate the behavior of these deep ocean flows. By incorporating data from long-term observatories, laboratory experiments, and remote sensing, researchers are building models that attempt to capture the full complexity of the system. These models must account for a multitude of factors, including the thermal and salinity gradients, the intricate topography of the seafloor, and the intermittent nature of seismic and tidal influences, to accurately represent the behavior of invisible currents. While these models are still in their early stages, they have already provided valuable insights into the mechanisms driving deep ocean circulation and the potential responses of these systems to environmental changes. The study of invisible currents is also revealing unexpected interactions between physical and chemical processes. For example, variations in the conductivity of seawater, which depend on temperature, salinity, and pressure, can affect how electromagnetic signals propagate through the deep ocean. These variations, in turn, influence the measurements recorded by magnetometers and other sensors. As researchers refine their methods for isolating the signals associated with deep ocean flows, they are beginning to disentangle the myriad factors that contribute to the overall noise. This effort not only improves our understanding of invisible currents, but also enhances our ability to monitor and predict other deep ocean phenomena, such as hydrothermal vent activity and sediment transport. Interdisciplinary collaboration is at the heart of this research. Oceanographers, geophysicists, chemists, and engineers are working together to develop new sensor technologies and analytical techniques. By combining their expertise, these teams are able to design instruments that can withstand the extreme conditions of the Hadal Zone while providing high-resolution data on the subtle movements of water deep below the surface. Recent advances in materials science have also led to the development of more robust sensors, capable of recording minute changes in electromagnetic fields and water movement over extended periods. In summary, the invisible currents conundrum represents one of the many subtle yet profound mysteries of the deep ocean. These currents, driven by density gradients, internal waves, and interactions with complex seafloor topography, are integral to the global circulation of heat, nutrients, and carbon. They are detected only with the aid of advanced instrumentation, which reveals a dynamic network of flows that is far more intricate than the surface currents we see on the ocean. The ongoing research into these hidden flows is gradually unraveling the underlying mechanisms, though many details remain elusive. The study of these currents not only deepens our understanding of the Earth's interior, but also carries important implications for climate science and marine ecology. As researchers continue to deploy advanced sensors, conduct long-term monitoring, and refine computational models, the picture of deep ocean circulation grows ever more detailed. Every new measurement, every subtle fluctuation in the electromagnetic field brings us one step closer to fully comprehending the invisible forces that shape our planet. Though imperceptible to the naked eye, these deep ocean currents are a testament to the power of natural processes operating under extreme conditions. They are a reminder that even in the darkest, most remote corners of the Earth, there exists an intricate interplay of physical and chemical forces, a hidden dance of water and energy that has persisted for millions of years. The mystery remains. not because it defies explanation, but because it challenges us to expand our knowledge and refine our tools in order to observe a world that is fundamentally different from the one at the surface. As you consider the subtle movements and quiet energy of these invisible currents, reflect on the vast, hidden mechanisms that govern the deep ocean. Each pulse of energy, each measured shift in water density, is a small part of a grand, global process that connects the deepest parts of the ocean to the surface and even to our atmosphere. The study of these currents is a reminder of the ongoing need to explore and understand every facet of our planet, no matter how remote or slow-moving it may seem. The conundrum of invisible currents is thus not merely a technical or academic puzzle. It is a window into the relentless, enduring forces that have shaped the Earth over geological time. It invites us to look deeper, beyond what is immediately visible, and to appreciate the complexity and beauty of the hidden world beneath the waves. Each discovery, each carefully recorded dataset, adds another piece to the intricate mosaic of our planet's deep ocean dynamics, and every new insight brings us closer to understanding the full story of our Earth's inner workings. Oarfish, often dubbed the doomsday fish, have long captivated both scientists and the public alike. These elongated, ribbon-like creatures are among the largest bony fish in the ocean, reaching lengths of up to 11 meters, yet they are rarely seen alive in their natural deep-sea habitat. Over the past few years, there has been a noticeable increase in oarfish strandings along various coastlines, an observation that has stirred both scientific curiosity and folklore. For centuries, cultures around the world have regarded the appearance of an oarfish as an omen, often foretelling earthquakes or other natural disasters. Despite these long-standing beliefs, the underlying causes of these strandings remain an unresolved puzzle. In their natural habitat, oarfish dwell in the mesopelagic to bathypelagic zones, far below the surface where sunlight barely penetrates. They are adapted to life in near total darkness, and their slender, serpentine bodies and shimmering scales allow them to blend into the faint light of the deep. Because of this, sightings in the wild are extremely rare. Most oarfish are only encountered when they become disoriented or are forced to the surface by factors that remain poorly understood. Occasionally, they wash up on beaches, and these events, when they occur in clusters or in unusual numbers, raise questions about possible triggers. One of the primary hypotheses centers on seismic activity. Folklore from several cultures links oarfish strandings with impending earthquakes. The theory is that the disturbances caused by seismic events, whether through changes in deep-sea pressure, shifting water currents, or even the release of gases from the seafloor, might disorient oarfish or force them upward, where they are more likely to end up on shore. Some studies have attempted to correlate the timing of oarfish beachings with seismic events. However, the scientific evidence remains inconclusive. While there are anecdotal reports of increased strandings preceding significant earthquakes, controlled studies have not yet demonstrated a statistically robust connection. The complexity of the deep-sea environment, where multiple factors such as water temperature, pressure, and ocean currents interact, makes it challenging to isolate a single cause. Another possibility is that environmental stressors may be driving these fish to the surface. Changes in water temperature or alterations in oceanic current patterns, possibly linked to climate change, could disrupt the delicate equilibrium of the deep-sea ecosystem. For instance, if the water becomes slightly warmer than usual, oarfish that are highly adapted to cold, deep water might experience physiological stress. This stress could impair their ability to navigate the vast, dark depths, causing them to stray toward the surface where they eventually wash ashore. Additionally, ocean noise pollution from increased shipping traffic and industrial activities might interfere with the oarfish's natural behavior, further contributing to their disorientation. The physical structure of the oarfish itself also plays a role in this puzzle. Their long, ribbon-like bodies are highly flexible but lack the robust musculature seen in more active, shallow water predators. This anatomy suggests that oarfish are not strong swimmers in the traditional sense. Rather, they are adapted to drifting with the slow, steady currents of the deep ocean. Any disruption in these currents, whether due to natural events like underwater landslides or human-induced changes, could have a significant impact on their ability to remain at their preferred depths. If displaced, an oarfish might find itself in a zone where it is more vulnerable to being carried toward the surface. The phenomenon of oarfish strandings has been documented in various parts of the world, from the coasts of California and Japan to the beaches of Australia. In some regions, strandings occur sporadically, while in others there appears to be a clustering of events. For example, several reports over the past few months have noted a surge in oarfish beachings along certain stretches of coastline, a pattern that has led some researchers to wonder whether there might be a common environmental trigger. Despite these observations, the sporadic nature of the strandings and the rarity of oarfish in their natural habitat make it difficult to conduct comprehensive studies. Field studies and deep-sea surveys continue to provide valuable data. Researchers employ a combination of techniques, including acoustic monitoring, satellite tracking, and direct sampling using ROVs and AUVs. Although direct observations of live oarfish in the wild remain scarce, data from stranded specimens offer insights into their health, age, and the conditions they experienced prior to beaching. Tissue analyses can reveal whether these fish were under stress from temperature fluctuations, oxygen depletion, or chemical imbalances in the water. Isotopic studies, for example, may indicate changes in the composition of the water they inhabited, suggesting that an environmental shift could have triggered their ascent. In some cases, researchers have also looked for correlations between oarfish strandings and other environmental phenomena. For instance, studies have examined whether there is a seasonal pattern to the strandings or if they coincide with periods of heightened seismic activity. While some correlations have been noted, the data is not yet robust enough to draw definitive conclusions. The challenge lies in the inherent variability of the deep-sea environment. Numerous factors can influence the behavior of oarfish, and isolating the impact of any single factor is a complex task. There is also a biological component to consider. Oarfish have a unique reproductive strategy that is not well understood. They are believed to spawn in deep waters, and the early life stages of these fish are rarely observed. It is possible that during spawning or post-spawning migrations, oarfish become more susceptible to being displaced by changes in water conditions. Additionally, natural mortality or predation could lead to a higher number of strandings at certain times of the year, further complicating the picture. The interplay between life history events and environmental stressors is an area that warrants further investigation. Historical records and folklore add another layer of intrigue. For centuries, sightings of oarfish have been shrouded in mystery, with many coastal cultures considering them harbingers of doom or omens of seismic upheaval. Ancient texts and local legends recount stories of these dinosaur fish appearing before catastrophic events such as earthquakes or tsunamis. While modern science has yet to confirm a causal relationship between oarfish strandings and seismic events, the persistence of these legends highlights the long-standing human fascination with these enigmatic creatures. Recent technological advances have enhanced our ability to monitor and study oarfish. High-resolution satellite imagery combined with sophisticated deep-sea sensors has allowed scientists to detect subtle changes in ocean conditions that may precede strandings. Researchers are now able to track water temperature, salinity, and even the movement of deep ocean currents with unprecedented precision. This wealth of data is beginning to reveal patterns that were previously hidden. For example, some studies have noted that strandings often occur during periods of anomalous deep ocean warming or during episodes of unusual current activity. These observations suggest that even slight perturbations in the normally stable deep-sea environment can have dramatic effects on species like the oarfish. Collaborative efforts among international research teams are crucial for making progress in this area. By pooling data from different regions, scientists hope to determine whether there is a global pattern to oarfish strandings or if the phenomenon is largely regional. Some research groups are now establishing long-term monitoring stations in areas known for frequent strandings, such as the coastal waters of Japan and California. These stations are equipped with acoustic sensors, water quality analyzers, and even automated cameras, all designed to capture the moment an oarfish approaches the surface. The data collected from these stations will be invaluable for understanding the environmental conditions that lead to strandings and for testing the various hypotheses that have been proposed. There is also a growing interest in using computational modeling to simulate the conditions that could lead to oarfish strandings. Models that incorporate oceanographic data, biological behavior, and even seismic activity are being developed to predict when and where strandings might occur. Although these models are still in their early stages, they hold the promise of providing a more comprehensive understanding of the factors at play. By comparing model predictions with observed strandings, researchers can refine their understanding of the underlying mechanisms and improve the accuracy of future forecasts. The mystery of the doomsday oarfish strandings remains unresolved, but each new study adds another piece to the puzzle. While folklore has long linked these strandings to seismic events, the scientific evidence remains inconclusive. It is likely that a combination of factors, including environmental stress, natural mortality, and even subtle changes in deep ocean circulation, contributes to these events. The challenge for researchers is to disentangle these factors and identify the precise triggers that force these deep-sea giants to stray from their dark, hidden realm and wash ashore. In summary, the sudden increase in oarfish strandings, often referred to in folklore as ominous or doomsday events, represents a complex interplay of biological, environmental, and possibly geological factors. These mysterious creatures, rarely seen in the deep ocean, sometimes appear at the surface in numbers that defy simple explanation. While some theories suggest that seismic activity may play a role in disorienting or triggering the ascent of oarfish, others point to environmental stressors such as water temperature changes, alterations in deep ocean currents, or even disturbances related to their reproductive cycles. The phenomenon remains a subject of active research, with ongoing efforts to correlate strandings with oceanographic and seismic data. Field observations, combined with advanced monitoring techniques and computational models, are gradually revealing the subtle cues that precede these events. Each strand of evidence, from the chemical composition of the water to the behavior of deep ocean currents and the timing of seismic tremors, offers a potential clue to the underlying mechanisms. Despite the progress made, the true cause of these strandings remains elusive, a reminder of the deep ocean's capacity to harbor mysteries that challenge our conventional understanding. As research continues, the doomsday oarfish strandings puzzle serves as both a scientific enigma and a window into the complex interplay between life and environment in the deep sea. The strandings are not simply random events, they are the result of a confluence of factors that have yet to be fully unraveled. While folklore has cast these events in a dramatic light, the reality is likely far more nuanced, a reminder that nature often operates in quiet, intricate ways that defy easy categorization. The ongoing studies and international collaborations promise to shed more light on this phenomenon. With each new stranding event, researchers gather more data, refine their models, and inch closer to understanding the conditions that cause these majestic, elusive creatures to be driven to the surface. Until then, the mystery endures, a complex puzzle at the intersection of biology, oceanography, and geology, inviting us to explore and appreciate the hidden depths of our planet's vast, mysterious oceans. Unexplained underwater gas pockets are one of the more intriguing phenomena observed on the ocean floor. These pockets, often detected as localized regions where dissolved gases suddenly accumulate and form discrete plumes or bubbles, challenge our understanding of seafloor dynamics and sediment chemistry. Detailed studies reveal that they can form through a combination of geological and biochemical processes that occur in the deep ocean. One of the most common gases in these pockets is methane, produced naturally by the microbial decomposition of organic material buried in sediments. In many continental margin environments, vast amounts of organic matter accumulate over millennia. Under high pressure and low temperature, anaerobic bacteria break down this material, releasing methane in the process. When the methane becomes saturated in the pore water of the sediment, it may start to coalesce into larger pockets. These pockets often appear as discrete, bubble-like accumulations that can be detected using echo sounders or remotely operated vehicles equipped with acoustic sensors. In some cases, the methane is trapped within a crystalline structure known as a gas hydrate, a compound where water molecules form a cage that encloses methane molecules. Gas hydrates are stable only under the extreme conditions of the deep ocean. However, if a change occurs in the surrounding environment, such as a shift in temperature, pressure, or even a change in sediment composition, the gas hydrates can destabilize rapidly. When this happens, the previously trapped methane is released in a sudden burst, creating a transient gas pocket. Such releases can lead to localized seafloor disturbances that are detectable as both physical and acoustic anomalies. High-resolution sonar imaging has provided clear evidence of these gas pockets. In many areas, sonar maps reveal regions where the seafloor appears pitted or dotted with bright spots, signatures that indicate the presence of gas bubbles rising through the sediment. Some studies have found that these gas pockets are not uniformly distributed but occur in clusters, often along fault lines or near areas of active fluid flow. The clustering suggests that structural features of the seafloor, such as fractures or small faults, may serve as conduits for the upward migration of methane. This is particularly evident in tectonically active regions where the stress on the crust can create new pathways for fluids to escape. Laboratory experiments and in situ measurements have shown that the formation of these gas pockets is influenced by several key factors. First, the rate of methane production in the sediment depends on the availability of organic material and the activity of methanogenic archaea. Second, the permeability of the sediment, the ability of fluids to move through the porous rock, plays a critical role. In low permeability sediments, methane can build up over time until it reaches a critical threshold, at which point it is released all at once. Third, changes in environmental conditions such as pressure or temperature, which might be triggered by seismic events or shifts in ocean currents, can force the trapped gas to escape. In many deep ocean settings, these gas releases are sporadic. Some releases occur continuously at a low rate, forming a steady plume, while others are episodic and violent, resulting in large bubbles that rise rapidly toward the surface. As the gas ascends, it expands due to decreasing pressure. By the time it reaches shallower waters, the bubbles may have merged or even burst, dispersing the gas into the overlying water column. This dispersion process is important because it influences the local chemistry of the seawater and can even affect marine life. For example, high concentrations of dissolved methane can lead to localized oxygen depletion, which in turn may create anoxic conditions that impact biological communities. Recent research using autonomous underwater vehicles has captured video footage of these phenomena in great detail. In one study, an AUV equipped with both high-resolution cameras and acoustic sensors recorded a series of gas bursts emanating from a sediment mound on the continental slope. The video shows gas bubbles emerging in rapid succession, sometimes forming a coherent plume that persists for several minutes before dissipating. Measurements taken from these recordings indicate that the size of the gas pockets can vary considerably, from small clusters of bubbles only a few centimeters across to larger, more expansive zones where gas saturates the entire sediment column. Advanced chemical analysis of water samples collected near these gas pockets has provided further insights. Researchers have measured concentrations of methane, carbon dioxide, and other trace gases, finding that in many cases the chemical signatures match those expected from biological methanogenesis. Isotopic ratios of carbon in the methane, for example, often fall within the range typical of microbial activity rather than thermogenic or abiotic processes. This isotopic evidence reinforces the idea that in many environments the gas pockets are a natural product of long-term biological degradation rather than the result of unusual or extraterrestrial processes. Another factor under investigation is the role of physical disturbances in triggering gas release. Seismic activity, even minor tremors, can alter the pressure conditions within the sediment and cause the sudden release of trapped gases. In areas with frequent low-magnitude earthquakes, gas pockets may be more common and the releases more dramatic. Observations from seafloor observatories have sometimes correlated bursts of acoustic energy with minor seismic events, suggesting that these disturbances may act as a catalyst for gas venting. Some researchers have also explored the possibility that the dynamics of these gas pockets could contribute to larger-scale geological processes. For example, the gradual accumulation and sudden release of methane from the seafloor are thought to play a role in the formation of submarine landslides. As gas accumulates beneath sediment layers, it reduces the overall stability of the sediment. If a significant gas pocket forms and then is abruptly released, the sudden change in buoyancy and sediment cohesion could trigger a landslide, a phenomenon that has implications for both seafloor morphology and tsunami generation. Despite the advances in our understanding, many aspects of underwater gas pockets remain enigmatic. The precise mechanisms by which gas is trapped and later released are still under active investigation, and the relative contributions of biological, chemical, and physical factors continue to be debated. Some regions show a consistent pattern of low-level gas seepage, while others exhibit intermittent, violent releases that are difficult to predict. The variability suggests that local conditions play a significant role in governing these processes, and that our current models may need refinement to account for the full range of observed behaviors. Interdisciplinary collaboration is key to unraveling these mysteries. Oceanographers, geochemists, and geophysicists are working together, often employing integrated sensor arrays that monitor not only gas concentrations but also temperature, pressure, and seismic activity. By correlating these diverse datasets, researchers hope to develop comprehensive models that can predict when and where gas pockets are likely to form. Such models have the potential to inform both our basic scientific understanding and practical applications, such as assessing the risks of submarine landslides or predicting localized changes in ocean chemistry that could affect marine ecosystems. One promising approach involves the use of long-term observatories deployed on the seafloor. These observatories, which can operate continuously for months or even years, collect high-resolution time series data that capture the episodic nature of gas releases. In one notable project, an array of sensors was installed on a sediment mound in the North Atlantic, an area known for active methane seepage. Over the course of a year, the observatory recorded a series of gas pulses that varied in intensity and frequency. Analysis of the data revealed periodic trends that appeared to be linked to tidal cycles, suggesting that even subtle changes in ocean currents might influence the dynamics of gas retention and release. In addition to natural triggers, some studies have investigated the possibility that human activities might influence the occurrence of underwater gas pockets. For instance, deep water drilling and other forms of resource extraction can disturb the sediment layers and alter the balance of forces that keep gas trapped. While the primary sources of methane in these environments are natural, any anthropogenic disturbance has the potential to exacerbate gas release, leading to a temporary increase in the number or intensity of gas pockets. Monitoring these changes is crucial for understanding not only the local environmental impacts, but also for informing sustainable practices in deep-sea resource management. The acoustic signature of underwater gas pockets is another area that has captured significant attention. When gas bubbles rise through the sediment and water, they produce distinct sounds, a series of clicks, pops, or low-frequency rumbles that can be detected by hydrophones. These acoustic signals provide an additional means of tracking gas release events even when direct visual observation is not possible. By analyzing the frequency, duration, and intensity of these sounds, researchers can infer details about the size of the gas pocket, the rate of gas release, and even the composition of the gas itself. Such acoustic monitoring complements chemical and physical measurements, offering a multidimensional view of these complex processes. While many underwater gas pockets have been well studied in regions like the Gulf of Mexico or the North Sea, there remain vast areas of the deep ocean where similar phenomena are likely occurring but have yet to be documented. The remote and inaccessible nature of the Hadal Zone means that our current picture is still incomplete. New technologies, such as enhanced AUVs and next-generation sensor arrays, are gradually extending our reach into these unexplored regions, promising to reveal more about the frequency, distribution, and behavior of underwater gas pockets. Ultimately, the mystery of unexplained underwater gas pockets is a window into the deep ocean's dynamic processes. These pockets are not anomalies in the sense of being inexplicable. Rather, they are the natural outcome of long-term interactions between organic matter, microbial activity, and geological forces. They serve as a reminder that the ocean floor is far from static. It is a living, evolving landscape where chemical, biological, and physical processes continuously interact. Each gas release event, each detected bubble, tells a part of the story of the Earth's interior, offering clues to the processes that have shaped the seafloor over geological time. In ongoing research, scientists are also examining how these gas pockets may influence the broader deep ocean environment. For instance, the release of methane, a potent greenhouse gas, can have localized effects on the ocean's chemistry, potentially altering pH levels and impacting deep-sea life. Understanding these interactions is crucial, not only for deep ocean science but also for broader climate studies, as the deep ocean plays a key role in the global carbon cycle. The study of underwater gas pockets thus represents a convergence of multiple scientific disciplines. It challenges researchers to consider the subtle interplay between geological and biological processes in an environment that is among the most extreme on Earth. Although many aspects of these phenomena remain elusive, each new discovery adds to our understanding of the intricate, interconnected systems that govern the deep ocean. As investigations continue, the data gathered from field surveys, laboratory experiments, and long-term observatories will help refine our models and ultimately provide a clearer picture of how these gas pockets form, evolve, and influence the seafloor environment. The insights gained from these studies are not only academically interesting, they also have practical implications for assessing geohazards, managing deep-sea resources, and understanding the complex feedbacks between the ocean and Earth's climate. In summary, unexplained underwater gas pockets are a natural but complex phenomenon arising from the interplay of organic decomposition, microbial activity, sediment dynamics, and changes in pressure and temperature. Their detection through advanced sensing technologies offers a glimpse into the hidden dynamic processes that continuously reshape the ocean floor. Although many questions remain, ongoing research is steadily illuminating the mechanisms behind these gas pockets, providing both fundamental insights and practical applications. Each recorded bubble, each transient plume, is a small piece of the deep ocean puzzle, an echo of the powerful forces that have been at work for eons. The study of these phenomena reveals not only the raw power of natural processes, but also the intricate beauty of the deep ocean, a realm where even the smallest gas pocket can tell a story of transformation, persistence, and the relentless march of time. Phantom seafloor structures present one of the more intriguing puzzles of deep ocean geology. These formations, detected primarily by high-resolution sonar and deep-sea mapping systems, appear as well-defined, often geometric shapes that stand out against the irregular, sediment-covered seafloor. In some regions, they manifest as nearly circular mounds, while in others, they occur as linear ridges or even complex, stepped formations. Although their origins have been debated for years, the prevailing evidence suggests that these structures are the product of natural processes, even if the precise mechanisms remain partially unresolved. One of the best documented examples is the so-called Baltic Sea anomaly. Discovered by a Swedish diving team during an expedition in the Gulf of Bothnia, this circular feature measures roughly 60 meters in diameter. Initial sonar images, with their sharp edges and regular outline, sparked widespread speculation that the anomaly might be man-made or even extraterrestrial in origin. However, subsequent geological analysis revealed that the structure is most likely a glacial deposit, a nodule or a concentration of rocks and sediment transported by glaciers during the last ice age. The materials sampled from the anomaly include granites, gneisses, and sandstones, which, when examined alongside the regional geology, support the hypothesis that the feature is a natural formation, molded by the slow but relentless forces of glacial erosion and sedimentation. Similar debates have arisen around other enigmatic formations, such as the Yonaguni Monument off the coast of Japan. Discovered by divers in 1986, the monument appears as a series of step-like structures and terraces carved into the underwater rock. Some early interpretations suggested that the formation might be the remnants of an ancient, submerged civilization. However, a detailed study of the rock's composition and morphology has led many geologists to argue that the features are entirely natural. Tectonic activity combined with long-term erosion and sediment compaction could produce the precise, geometric outlines that characterize these structures. In the case of Yonaguni, the sharp angles and apparent steps are now understood to be the result of natural fracturing in hard, sedimentary rock, further modified by currents and biological activity over thousands of years. Beyond these high-profile cases, a variety of phantom seafloor structures have been identified in diverse deep ocean environments. On continental slopes and abyssal plains, for example, researchers have noted dome-shaped mounds that rise smoothly from the surrounding sediment. Many of these mounds are interpreted as the products of carbonate precipitation. In areas where organic material is abundant, methane generated by the decay of buried life forms can migrate upward through the sediment. When this methane encounters sulfate-rich seawater, anaerobic oxidation of methane occurs, producing bicarbonate ions. These ions then combine with calcium to form calcium carbonate, which slowly precipitates and accumulates over time. The result is a hard, rounded mound that often exhibits a surprisingly uniform, almost sculptural appearance. The process is gradual, a slow accumulation over thousands to millions of years, and is influenced by local variations in temperature, pressure, and chemical composition. Another natural mechanism that may give rise to these phantom structures is the formation of pockmarks on the seafloor. These pockmarks are created when subsurface fluids, such as methane or water, escape violently from the sediment. The sudden expulsion of fluid erodes the surrounding material, forming circular depressions. In some cases, the collapse of these depressions, coupled with subsequent sediment deposition, can produce raised, mound-like features. While these features are often temporary on human timescales, Under the right conditions, they can become stable parts of the seafloor topography. The regularity of many phantom seafloor structures has long fascinated scientists. Unlike the random, chaotic patterns one might expect from natural erosion, these structures often exhibit symmetry and a level of uniformity that suggest a self-organizing process. Laboratory experiments have demonstrated that under controlled conditions, mineral-rich solutions can precipitate into nearly perfect spheres or domes when subject to rapid cooling and high pressure. Such experiments indicate that surface tension plays a key role in driving particles to adopt a spherical shape, a process analogous to the formation of raindrops in the atmosphere. However, the deep ocean is a far more complex environment than any laboratory, with numerous variables such as fluid turbulence, sediment load, and varying chemical gradients, all influencing the final form of the structure. Advanced remote sensing technologies have been pivotal in revealing the existence and nature of these seafloor structures. Multi-beam sonar systems mounted on research vessels and autonomous underwater vehicles generate three-dimensional maps of the seafloor with remarkable detail. These maps often reveal features that would otherwise remain hidden beneath thick layers of sediment. In some regions, the mounds appear as isolated, solitary features, while in others, they form clusters or align along fault lines and fracture zones, hinting at underlying tectonic controls. Such spatial patterns are crucial for developing models of fluid migration and sedimentation processes that might account for the formation of these enigmatic structures. The composition of these mounds has been analyzed using a range of techniques. When samples are collected by remotely operated vehicles, they are subjected to X-ray diffraction and scanning electron microscopy to determine their mineral content. Many mounds are found to be rich in carbonate minerals like calcite or aragonite, consistent with the process of biogenic precipitation from methane oxidation. In areas associated with hydrothermal venting, the presence of sulfide minerals alongside carbonates provides further evidence that complex chemical reactions are at work. Isotopic analyses of carbon and oxygen within the carbonate layers offer additional clues about the temperature and chemistry of the fluids from which the minerals precipitated, helping to reconstruct the environmental conditions at the time of formation. There is, however, a degree of variability among phantom seafloor structures. Not all mounds conform neatly to the carbonate precipitation model. In some cases, the structures appear to be more influenced by mechanical processes such as sediment compression and fluid expulsion than by chemical precipitation alone. These differences underscore the fact that multiple mechanisms may be responsible for the wide array of geometric formations observed on the deep ocean floor. Even within a single region, variations in local geology, fluid flow, and sediment supply can lead to the development of distinct structural types. Interdisciplinary collaborations have become essential for advancing our understanding of these formations. Geologists, chemists, and oceanographers are pooling their expertise to conduct integrated studies that combine direct sampling with high-resolution mapping and advanced computational modeling. In some of the world's most active research areas, such as the Mid-Atlantic Ridge and the hydrothermal fields of the East Pacific Rise, long-term observatories have been deployed that continuously monitor the seafloor. These observatories record subtle changes in the acoustic, chemical, and electromagnetic properties of the environment, providing a dynamic picture of the processes that shape phantom seafloor structures over time. The interplay between natural forces that create these structures is subtle and often gradual. Over time, even small variations in environmental conditions can lead to significant differences in the morphology of a mound. For instance, a slight increase in the concentration of dissolved minerals may accelerate the rate of carbonate precipitation, resulting in a more prominent, sharply defined mound. Conversely, a reduction in the availability of methane or calcium could slow the growth of the structure, leading to a more subdued, less distinct formation. By carefully studying these variations, scientists hope to build a comprehensive model of deep ocean sedimentation and chemical precipitation that can account for the diversity of phantom seafloor structures observed around the globe. One intriguing possibility that has been raised is that some of these structures might record episodes of intense geological activity. Sudden releases of methane from gas hydrates triggered by warming temperatures or shifts in pressure could lead to rapid carbonate precipitation and the formation of mounds in a relatively short period of time. These episodic events might be captured in the layered structure of a mound, much like tree rings record years of growth. By analyzing the stratigraphy of these formations, researchers can potentially infer the timing and magnitude of past geological events, offering a window into the dynamic history of the deep ocean. Despite the advances made in deep-sea exploration and mapping, many aspects of phantom seafloor structures remain elusive. The sheer scale and remoteness of the deep ocean make it challenging to obtain high-quality data across all regions. Some areas have been mapped extensively, while others remain largely unexplored. Furthermore, the processes that form these structures can be influenced by transient phenomena, such as episodic fluid flows or short-term tectonic events, that are difficult to capture in a single survey. This inherent variability means that our understanding of these formations is still evolving, and each new expedition has the potential to reveal unexpected features that challenge existing theories. The ongoing study of phantom seafloor structures is not merely an academic pursuit, it has practical implications as well. In some regions, these mounds are associated with valuable mineral deposits or even hydrocarbon reservoirs. Understanding their formation can aid in assessing the potential for resource extraction, while also ensuring that any such activities are conducted in an environmentally responsible manner. Additionally, insights gained from studying these structures can inform our broader understanding of sedimentary processes, fluid dynamics, and even climate change. Since the deep ocean plays a critical role in regulating Earth's carbon cycle. In many respects, the mystery of phantom seafloor structures is a celebration of nature's ability to create order out of chaos. Despite the seemingly random assortment of sediments and rocks on the ocean floor, these structures emerge as coherent, often symmetrical features, a testament to the persistent, self-organizing forces at work beneath the waves. They remind us that even in the most inhospitable and extreme environments, natural processes can produce forms of striking beauty and complexity. The fact that these structures are still not fully understood, despite decades of study, only adds to their allure. Current research efforts continue to focus on detailed mapping and sampling campaigns, using a combination of manned and unmanned vehicles to gather data from these remote regions. As technology advances, new sensors and analytical techniques are being developed that promise to reveal even finer details about the composition and structure of these mounds. Over time, the accumulation of high-quality data from diverse locations around the globe will likely lead to a more unified theory of their formation. A theory that can account for the wide range of shapes and sizes observed, as well as their distribution across the seafloor. For now, phantom seafloor structures remain one of the deep ocean's most captivating enigmas. Their quiet, persistent presence on the ocean floor, revealed only through the lens of advanced sonar and deep-sea imaging, speaks to the enduring mystery of our planet's hidden depths. Each formation, with its distinctive shape and subtle texture, is a reminder of the complex interplay of physical, chemical, and sometimes biological forces that continuously sculpt the Earth in ways that are both gradual and profound. In the silent, dark realm of the Hadal Zone, where human eyes rarely venture and where pressures defy imagination, these structures stand as monuments to natural history. They are the quiet legacy of processes that have operated long before the advent of modern technology and will continue long after we have ceased to explore their domain. Their study offers a glimpse into a world that is fundamentally different from our own, a world governed by the slow rhythms of geological time and the relentless, unseen power of the deep. And so, as the investigation of phantom seafloor structures presses on, every new finding adds a brushstroke to the larger canvas of deep ocean science. The emerging picture is one of gradual evolution, marked by episodes of sudden change and punctuated by the subtle whisper of natural forces working in tandem. Though much remains to be discovered, the quest to understand these mysterious formations has already deepened our appreciation of the hidden, intricate workings of the Earth's most remote environments. Deep in the Hadal Zone, those abyssal depths beyond 6,000 meters where the water pressure crushes almost every human-made object, researchers have recorded a series of low-frequency electromagnetic signals that defy conventional expectations. In this extreme environment, where temperatures barely rise above freezing and darkness is nearly complete, sensitive instruments sometimes register bursts of energy that seem to arise from the very fabric of the deep ocean. One of the most notable findings is the occurrence of transient electromagnetic pulses that appear to emanate from specific patches of the seafloor. These pulses are detected by arrays of magnetometers and other electromagnetic sensors deployed on autonomous underwater vehicles (AUVs) and remotely operated vehicles (ROVs. Unlike the steady geomagnetic field generated by the Earth, these signals come in short bursts or as subtle, rhythmic hums that persist for several seconds to minutes. Their occurrence does not correlate with typical sources such as ship traffic or known natural electrical discharges, leading scientists to suspect that a combination of deep ocean processes is at work. A leading hypothesis involves the dynamic activity at hydrothermal vent fields. At these vents, superheated, mineral-rich water is expelled from the Earth's crust into the near-freezing ambient seawater. This rapid temperature drop triggers the formation of bubbles as dissolved gases rapidly come out of solution. The violent mixing of the hot vent fluid with the cold water creates turbulent currents and cavitation events, the rapid formation and collapse of bubbles. These processes can generate shock waves and, importantly, drive electrokinetic phenomena. In electrokinetics, the movement of an electrically conductive fluid through porous, charged sediment produces small electric currents. These currents, in turn, generate local magnetic fields that fluctuate in time, sometimes resulting in the low-frequency pulses that are recorded by deep ocean observatories. Another factor potentially contributing to these anomalies is the unique mineralogy found on the seafloor in the Hadal Zone. Rocks in these extreme depths often contain high concentrations of iron oxides and other magnetic minerals. Over geologic time, as these minerals weather and recrystallize under high pressure, they may develop localized variations in their magnetic properties. When deep ocean currents or tectonic shifts disturb these regions, the resulting movement can create brief but measurable electromagnetic disturbances. The interplay between natural fluid dynamics and the magnetic characteristics of the seafloor gives rise to a sort of electromagnetic background music that is both complex and, in a way, surprisingly ordered. Laboratory experiments have offered additional insight. By simulating the conditions of the Hadal Zone in pressurized tanks, scientists have recreated some of the electrokinetic effects observed in the field. In these controlled settings, researchers heat mineral-rich solutions to mimic the superheated vent fluids and then rapidly cool them under high-pressure conditions. As the solutions cool, dissolved gases form tiny bubbles which rapidly oscillate and collapse, producing electromagnetic signals similar in frequency and duration to those detected in situ. Such experiments not only confirm that these processes can indeed generate detectable signals, but also help to calibrate the instruments used in deep ocean research. The propagation of these electromagnetic pulses is influenced by the unique properties of seawater at extreme depths. Seawater, while an excellent conductor of electricity, exhibits variable conductivity depending on temperature, salinity, and pressure. In the Hadal Zone, near-freezing temperatures and immense pressures create conditions in which even minor electrical disturbances can travel considerable distances without significant attenuation. This means that a localized event, like a sudden release of methane from a vent or the collapse of a bubble cluster, can produce a signal detectable by sensors located kilometers away. The ability to record such signals provides a valuable window into the underlying physical and chemical processes that occur in these remote regions. Yet, despite the progress made, many questions remain. One challenge is separating the electromagnetic signals generated by hydrothermal vent activity from those caused by other phenomena such as seismic events, sediment movement, or even deep-sea biological activity. The deep ocean is replete with overlapping sources of noise, a steady hum from the Earth's magnetic field, sporadic microseismic tremors, and the faint signals produced by deep-sea fauna. Advanced signal processing methods, including spectral and time series analyses, are being used to distinguish the unique signatures associated with bubble collapse or fluid turbulence from the general acoustic background. Researchers are also engaged in long-term monitoring of these anomalies. In certain areas known for active hydrothermal venting or tectonic activity, permanent deep ocean observatories have been installed. These sensor networks continuously record data over months and years, revealing both gradual trends and sudden shifts in the electromagnetic environment. For instance, a sudden spike in the signal intensity might correlate with a minor tectonic movement or an episodic increase in vent output. Such correlations can help refine our understanding of the processes at play and may even serve as early warning indicators for deeper geophysical events, such as undersea earthquakes or volcanic eruptions. Another intriguing possibility is that these electromagnetic signals might, in some cases, be influenced by the behavior of gas hydrates. Gas hydrates are crystalline compounds in which water molecules form a cage-like structure that traps methane. They are stable only under the high-pressure, low-temperature conditions typical of the deep ocean. However, if the local pressure or temperature changes slightly, these hydrates can destabilize and release methane in a sudden burst. The dissociation of gas hydrates alters the local chemical environment and can generate transient electrical currents, adding another layer of complexity to the electromagnetic signature of the Hadal zone. The study of these anomalies is interdisciplinary by nature. Oceanographers, geophysicists, chemists, and engineers work together to integrate data from multiple sources. For instance, by combining readings from hydrophones, magnetometers, and temperature sensors, scientists can construct a detailed, multidimensional picture of the local environment. This holistic approach allows for more accurate reconstruction of the events that generate the signals, such as the precise timing of bubble formation or the spatial distribution of mineral deposits. Recent field expeditions have employed autonomous underwater vehicles that are equipped with both optical cameras and electromagnetic sensors. These vehicles descend into the Hadal zone and capture high-resolution images and sensor data that reveal not only the physical structure of the seafloor but also the subtle variations in the electromagnetic field. In some missions, the AUVs have recorded sequences of pulses that appear to have a rhythmic quality, almost as if the deep ocean itself is communicating through these signals. These observations are still under active analysis, and while preliminary models suggest that they arise from a combination of fluid dynamics and mineral interactions, the precise details continue to elude full explanation. The fact that such electromagnetic anomalies can be recorded in the Hadal zone has practical implications as well. If these signals can be reliably correlated with specific geological or chemical events, they might eventually be used as a diagnostic tool for monitoring deep ocean processes. For example, sudden changes in the signal patterns could alert researchers to shifts in vent activity, changes in sediment composition, or even emerging tectonic stresses. Over time, this could lead to the development of new methods for deep ocean exploration and hazard assessment, tools that are invaluable in an environment as remote and extreme as the Hadal zone. Despite these promising avenues, the deep ocean remains a challenging frontier. The electromagnetic anomalies, though fascinating, are only one part of a broader tapestry of mysterious phenomena that occur at extreme depths. The Hadal zone, by virtue of its inaccessibility, continues to harbor secrets that challenge even our most advanced technologies. Each new discovery raises as many questions as it answers, underscoring the complexity of the natural processes that shape our planet's interior. In the end, the electromagnetic signals recorded in the Hadal zone serve as a subtle reminder of the dynamic, ever-changing nature of the deep ocean. They are the soft, persistent echoes of processes that have been at work for millions of years, processes that, despite our technological prowess, remain only partially understood. These signals are not anomalies in the sense of being inexplicable or unnatural. Rather, they are a natural byproduct of the extreme conditions and unique interactions that occur in the abyss. As researchers continue to refine their techniques and deploy even more sophisticated instruments, the hope is that one day these electromagnetic pulses will reveal all their secrets. For now, they offer us a glimpse into a world that is both alien and familiar, a world where the fundamental forces of physics and chemistry come together in a quiet, relentless symphony beneath the waves. Every recorded pulse, every measured fluctuation adds to our growing understanding of this hidden realm. With each new expedition and every new dataset, the picture of the Hadal zone becomes a little clearer, a little more detailed. Yet the profound mystery remains, a testament to the beauty and complexity of the natural world. In the silent depths, the electromagnetic anomalies continue their steady rhythm, a whisper of the forces that have shaped the Earth since time immemorial, inviting us to listen, to learn, and to marvel at the wonders of our planet's most extreme environment. Underwater volcanic smoke is a fascinating phenomenon that occurs during submarine eruptions, and it offers a window into the dynamic processes shaping our planet's ocean floors. When an underwater volcano erupts, the molten rock, magma, erupts into the cold seawater. Although it might seem counterintuitive to speak of smoke beneath the waves, what is observed is a plume composed of gas bubbles, fine ash, and suspended particles that spread upward through the water column. In these eruptions, the heat of the magma rapidly heats the surrounding water, causing dissolved gases to come out of solution and form bubbles. Under the crushing pressure of the deep ocean, these bubbles may coalesce into a dense column that, in certain lighting conditions, appears as a dark, diffuse plume rising from the seafloor. Unlike smoke on land, which is composed of combustion products, the smoke in an underwater eruption is the product of physical and chemical processes. For instance, volcanic gases such as carbon dioxide, sulfur dioxide, and hydrogen sulfide are released and, together with entrained volcanic ash and mineral particles, create the visible plume. One well-documented example of this phenomenon is the eruption of the West Mata volcano in the Lao Basin near Tonga in 2009. ROVs captured dramatic footage of a plume of discolored water rising from the vent, with the expelled materials forming a column that spread into the surrounding dark ocean. Detailed studies of such plumes reveal that the temperature difference between the superheated vent fluids and the near-freezing ambient water drives rapid chemical reactions. As the hot fluids mix with the cold seawater, mineral precipitates, often sulfide compounds, begin to form. These precipitates add opacity and color to the plume, sometimes giving it a smoky appearance. The behavior of these plumes is governed by the interplay of several factors. First, the density contrast between the heated, gas-rich fluid and the surrounding cold water drives vigorous buoyant flow. This buoyancy causes the plume to rise, much like a thermal plume rising through the air. However, as the plume ascends, it encounters cooler, denser water that gradually mixes with it. This mixing dilutes the concentration of gases and particles, causing the plume to spread laterally and eventually dissipate into the surrounding ocean. The rate at which this happens depends on the initial temperature and composition of the erupted material, the ambient water temperature, and local current conditions. Hydrothermal vent fields are often hotspots for this kind of activity. At these sites, the seafloor is punctuated by vents that continuously release hot, chemically enriched water. Although many vents produce relatively steady plumes, episodic bursts of activity can create sudden, dramatic smoke events. During an intense burst, the plume may rise rapidly, reaching heights of several hundred meters above the vent before dispersing. Such events have been detected by deep-sea observatories that combine acoustic measurements with direct water sampling. The acoustic signatures of these eruptions can include a series of low-frequency pulses that mirror the sudden release of energy as gas bubbles expand and collapse in the turbulent water. Another interesting aspect of underwater volcanic plumes is their chemical evolution. Initially, the erupted material is rich in reduced compounds like hydrogen sulfide. However, as the plume mixes with oxygenated seawater, these compounds oxidize, leading to the formation of sulfates and other oxidized minerals. In some cases, this transformation produces visible changes in the color and opacity of the plume. For example, a plume might begin as a dark, almost black column and gradually become lighter and more diffuse as chemical reactions progress. By analyzing water samples from various heights within the plume, researchers can reconstruct the sequence of chemical changes that occur during the mixing process. This chemical evolution not only provides insights into the dynamics of the eruption itself, but also offers clues about the broader geochemical cycles operating in the deep ocean. Deep-sea chemical plumes also have a profound impact on the local ecosystem. The chemicals released during an eruption can serve as nutrients for chemosynthetic organisms, bacteria and archaea, that derive energy from chemical reactions rather than sunlight. In cold seep environments where similar chemical plumes are common, these microorganisms form the base of an entire ecosystem, supporting species such as mussels, clams, and tube worms. While the explosive energy of a submarine eruption may initially disrupt local life, over time, the deposition of minerals and the alteration of water chemistry can create new niches for life to flourish. In this way, underwater volcanic smoke is not merely a destructive force, but also a catalyst for renewal in the deep ocean. Technological advances have significantly enhanced our ability to study these phenomena. Modern ROVs and AUVs are equipped with high-definition cameras, chemical sensors, and multi-beam sonar systems that can capture detailed images and data of both the eruption plume and the surrounding seafloor. These tools have allowed scientists to observe plumes in real time, track their evolution, and even measure the precise concentrations of dissolved gases and minerals within them. In one recent expedition, an array of sensors was deployed around an active vent, recording the temperature, pressure, and chemical composition of the plume at various depths. The data revealed that the plume maintained a distinct signature, a rapid change in temperature and a spike in dissolved hydrogen sulfide, that gradually faded as the plume ascended and mixed with the ambient water. In addition to in situ measurements, laboratory experiments have played a key role in elucidating the processes behind underwater volcanic plumes. Researchers have simulated the conditions of an underwater eruption by heating mineral-rich solutions and then rapidly cooling them under high pressure. These experiments have demonstrated that the interplay between rapid cooling and turbulent mixing can indeed produce plumes that share many characteristics with those observed in the deep ocean. Such controlled studies help refine our understanding of the key parameters, such as initial temperature, gas composition, and mixing rate that determine the plume's behavior. Moreover, they allow scientists to test the reliability of their remote sensing techniques and to calibrate the instruments used in deep-sea exploration. Despite the progress made, many challenges remain in fully understanding underwater volcanic smoke. The deep ocean is an environment of immense complexity, where multiple processes interact simultaneously. Disentangling the contributions of buoyant flow, chemical reactions, and biological activity to the overall appearance of the plume requires both long-term monitoring and high-resolution data. Advanced signal processing techniques, combined with continuous observations from permanent deep ocean observatories, are gradually revealing the subtle patterns and variations within these plumes. Researchers are beginning to identify specific triggers, such as changes in vent output or minor seismic events, that correlate with sudden shifts in plume dynamics. Such correlations are crucial for developing predictive models that can forecast the behavior of underwater volcanic plumes. There is also growing interest in the potential broader impacts of these plumes. Because they are capable of transporting dissolved chemicals over long distances, they play a significant role in the global cycling of elements such as carbon, sulfur, and iron. For example, when a plume rises and eventually disperses at shallower depths, it can deliver nutrients that stimulate surface productivity. Conversely, the release of gases like methane, a potent greenhouse gas, can have implications for climate regulation. Understanding how these plumes contribute to the larger oceanic and atmospheric systems is an area of active research, one that bridges the fields of geochemistry, oceanography, and climate science. Interdisciplinary collaboration is essential in unraveling the mysteries of underwater volcanic plumes. Teams of scientists from diverse fields are working together to integrate data from remote sensing, direct sampling, laboratory experiments, and computational models. By combining these different approaches, researchers aim to construct a comprehensive picture of the plume dynamics, from the moment the volcanic material is erupted, through its rapid chemical transformation, to its eventual dispersion into the ambient water. Such a holistic view is critical not only for understanding the plumes themselves, but also for gaining insights into the complex processes that govern the deep ocean as a whole. The study of underwater volcanic smoke phenomena is a testament to the dynamic and ever-changing nature of our planet's interior. These plumes are not isolated events. They are part of a continuous process of energy and matter exchange that has been occurring for millions of years. The transient yet measurable signals generated by these plumes provide a rare glimpse into the deep-sea environment, a world where extreme conditions give rise to processes that challenge our conventional understanding of chemistry and physics. In summary, underwater volcanic smoke is a complex phenomenon resulting from the rapid interaction between superheated, mineral-rich fluids and the cold, dense seawater of the deep ocean. The resulting plumes, composed of gas bubbles, ash, and suspended particles, are shaped by a combination of buoyant forces, chemical reactions, and turbulent mixing. These plumes not only offer insights into the mechanics of submarine eruptions, but also play a critical role in the deep ocean ecosystem and global biogeochemical cycles. Through advanced field measurements, laboratory experiments, and computational modeling, scientists are steadily uncovering the processes behind these enigmatic plumes. Each new observation adds to our understanding of how deep ocean volcanic activity influences everything from local marine life to global climate patterns. The ongoing research into these chemical plumes stands as a reminder that the deep ocean remains one of Earth's last unexplored frontiers, a realm where even the seemingly ephemeral smoke from an underwater eruption can carry profound implications for our understanding of the planet. Every plume, every burst of mineral-rich fluid is a chapter in the deep ocean's long story, inviting us to explore, analyze, and appreciate the intricate interplay of natural forces that shape our world. Deep-sea chemical plumes are one of the ocean's most dynamic and intriguing phenomena. In many regions of the deep ocean, especially near hydrothermal vent fields and cold seep areas, dissolved chemicals are released from the seafloor, forming diffuse, sometimes strikingly visible plumes that rise and spread through the water column. These plumes consist of a complex mix of dissolved gases, minerals, and other compounds that are injected into the overlying water. Their study has shed light on the processes that drive deep ocean chemistry and the unique ecosystems that thrive in these extreme environments. In many cases, chemical plumes originate at hydrothermal vents, sites where superheated, mineral-rich water is expelled from the Earth's crust. At these vents, water is heated to temperatures that can exceed 350 degrees Celsius and is saturated with dissolved metals such as iron, manganese, and copper, along with dissolved gases like hydrogen sulfide and carbon dioxide. When this superheated fluid meets the near-freezing ambient seawater, rapid cooling induces a series of chemical reactions. For example, hydrogen sulfide may oxidize to form sulfate, while dissolved metals can precipitate out as sulfide minerals. The mixing process creates a plume that can extend for kilometers above the vent. These plumes are not static, they are continuously diluted and transformed by turbulent mixing, which gradually disperses the chemicals into the broader water mass. Cold seep areas provide another source for deep-sea chemical plumes. In these regions, methane, produced by the microbial decomposition of organic matter in sediments, migrates upward through the seafloor. When methane-rich fluids reach the sediment-water interface, they often carry with them other compounds, including hydrogen sulfide, ammonia, and various trace metals. The resulting plume supports chemosynthetic communities where specialized bacteria oxidize methane or hydrogen sulfide to fix carbon and produce energy. These microorganisms form the base of an entire ecosystem, giving rise to unique assemblages of organisms such as clams, mussels, and tube worms that rely entirely on chemical energy rather than sunlight. The chemical composition of these plumes can vary significantly depending on their source. At hydrothermal vents, the plumes typically have elevated concentrations of dissolved metals, hydrogen sulfide, and silica, whereas at cold seeps, methane is often the dominant component. Measurements taken using conductivity temperature depth, CTD, sensors, water samplers, and in situ chemical analyzers have allowed scientists to quantify the concentrations of various elements and compounds within these plumes. For instance, dissolved iron, an essential nutrient for phytoplankton growth, can be enriched in hydrothermal plumes, thereby influencing primary production even at the ocean surface when these deep waters eventually upwell. In cold seep plumes, isotopic analysis of methane often points to a biological origin, distinguishing biogenic methane from thermogenic sources that are generated by the thermal breakdown of organic matter deep within the Earth. Advanced imaging techniques, including laser-induced fluorescence and high-resolution spectroscopy, have further enhanced our ability to study these plumes. By analyzing the spectral signatures of the dissolved compounds, researchers can infer not only their concentrations but also the chemical reactions that are occurring as the plume disperses. In some studies, scientists have observed that as a plume rises, its chemical composition evolves. The high concentrations of reduced compounds like hydrogen sulfide gradually diminish as they oxidize, while secondary products such as sulfate increase. This temporal evolution provides insight into the rates of chemical reactions and the overall mixing processes occurring in the deep ocean. One fascinating aspect of deep-sea chemical plumes is their influence on marine ecosystems. The chemicals released in these plumes, particularly methane and hydrogen sulfide, create localized environments where chemosynthetic organisms can thrive. In the absence of sunlight, these organisms rely on the oxidation of inorganic molecules to fix carbon, forming the base of a food web that is entirely independent of photosynthesis. The communities that develop around these plumes are often extraordinarily diverse, featuring organisms that are found nowhere else on Earth. Moreover, the plumes themselves can act as conduits, transporting nutrients and energy from the deep sea floor to higher layers of the water column. This vertical mixing can have far-reaching effects on ocean chemistry and even contribute to the global carbon cycle by affecting the distribution of greenhouse gases. Deep-sea chemical plumes also have practical implications beyond supporting unique ecosystems. For example, the detection and monitoring of these plumes can serve as natural tracers for studying ocean circulation patterns. Because plumes can persist for extended periods and travel great distances, they provide valuable information about the movement of water masses in the deep ocean. In some regions, scientists use the dispersion of chemical plumes as a natural dye to track deep ocean currents, revealing the hidden pathways by which heat, nutrients, and dissolved gases are redistributed on a global scale. In addition to natural processes, human activities may sometimes influence the occurrence and composition of chemical plumes. Deep water drilling, mining, and even the disposal of industrial waste can introduce pollutants into the ocean, sometimes generating plumes that are detectable far from their source. Distinguishing between naturally occurring plumes and those resulting from anthropogenic activities is a key challenge for environmental scientists. Careful chemical analysis combined with isotopic measurements can often help determine the origin of a plume. For instance, the ratios of certain isotopes in methane or carbon dioxide can indicate whether they were produced by biological activity in the sediment or derived from the combustion of fossil fuels. Field studies in regions such as the Mid-Atlantic Ridge, the East Pacific Rise, and the Gulf of Mexico have provided rich datasets on deep-sea chemical plumes. In one long-term study, an array of sensors was deployed near a known hydrothermal vent field. Over the course of several months, these instruments recorded continuous data on temperature, chemical composition, and fluid flow. The data revealed that plumes from the vents exhibited not only a predictable pattern of dilution but also episodic bursts corresponding to sudden changes in vent activity, perhaps triggered by minor seismic events or fluctuations in the magmatic heat source. Such episodic events underscore the dynamic nature of these deep ocean systems, where even subtle variations in environmental conditions can result in significant chemical changes. Laboratory simulations have been an essential complement to field studies. By recreating the high-pressure, low-temperature conditions of the deep ocean, researchers can better understand the kinetics of chemical reactions that occur within plumes. In controlled experiments, mineral-rich solutions are rapidly cooled under pressure to mimic the mixing of hydrothermal fluids with ambient seawater. These experiments have shown that the rate of chemical transformation can be surprisingly rapid, with significant changes in the concentration of dissolved species occurring within minutes. Such findings help to explain the rapid evolution of a plume's chemical signature as it rises and mixes with the surrounding water. Another area of ongoing research is the role of biological processes in modifying deep-sea plumes. Microorganisms that inhabit the deep-sea floor are capable of catalyzing chemical reactions, thereby altering the composition of the water. In many cold seep environments, microbial communities rapidly consume methane, transforming it into carbon dioxide in water, a process that not only supports chemosynthetic life but also influences the overall chemistry of the plume. Similarly, bacteria may facilitate the oxidation of hydrogen sulfide, reducing its concentration and contributing to the formation of sulfate. The interplay between microbial metabolism and chemical transformations in these plumes is an active area of investigation, with significant implications for understanding both deep ocean ecology and global biogeochemical cycles. Advanced remote sensing techniques, including satellite measurements of sea surface height and color, have also begun to play a role in studying deep ocean plumes. While satellites cannot directly observe the chemical composition of water at depth, they can detect changes at the ocean's surface that may be linked to underlying processes. For example, areas where deep water rich in dissolved minerals upwells can show distinct color patterns due to the concentration of suspended particles. These surface anomalies, when correlated with in situ data, can help map the extent and influence of deep-sea plumes on broader ocean circulation. The study of deep-sea chemical plumes is not only a matter of scientific curiosity, it has practical applications as well. Understanding the dynamics of these plumes is crucial for assessing their impact on deep ocean ecosystems, particularly in regions where human activities, such as deep water drilling and mining, occur. Moreover, these plumes can influence the global carbon cycle by affecting the distribution and sequestration of greenhouse gases. Insights gained from studying the formation, evolution, and dispersion of chemical plumes can improve models of ocean circulation and climate change, leading to more accurate predictions of future environmental conditions. Interdisciplinary collaboration remains a cornerstone of this research. Oceanographers, geochemists, microbiologists, and engineers work together to deploy and calibrate sensors, conduct field experiments, and develop computational models that simulate the complex interactions within plumes. These collaborative efforts have led to significant breakthroughs, yet many questions remain. For instance, The precise mechanisms that govern the transition from a concentrated plume near a vent to a diffused signal in the open ocean are still not fully understood. Similarly, while the role of microbial activity is increasingly recognized, the full extent to which it modifies the chemical composition of a plume over time is an area of active study. One particularly promising avenue is the integration of real-time data from multiple sensor networks. Deep ocean observatories, equipped with instruments that measure temperature, chemical composition, fluid flow, and even acoustic signals, are now capable of providing continuous, high-resolution datasets that capture the dynamic behavior of chemical plumes. By analyzing these datasets with advanced statistical and computational methods, scientists can identify subtle patterns and correlations that were previously hidden in the noise. These efforts are gradually building a more complete picture of how deep ocean plumes form, evolve, and interact with their environment. While much remains to be learned about deep-sea chemical plumes, the progress made so far has already significantly advanced our understanding of deep ocean processes. The interplay of physical, chemical, and biological factors in these plumes is a vivid reminder that the deep ocean is far from a static, unchanging environment. Instead, it is a dynamic system where rapid chemical reactions, driven by extreme conditions and intricate fluid dynamics, continually reshape the seafloor and influence global climate patterns. In essence, deep-sea chemical plumes are a natural expression of the Earth's internal energy and its relentless drive to redistribute heat and matter. These plumes serve as conduits, transporting dissolved chemicals from the very depths of the seafloor to the higher layers of the ocean, where they can eventually affect surface processes and even global climate. The study of these phenomena reveals not only the power and complexity of natural processes in the deep ocean, but also their interconnectedness with the rest of our planet. As researchers continue to refine their techniques, combining long-term observational data, laboratory experiments, and sophisticated modeling, the mystery of deep-sea chemical plumes is slowly being unraveled. Each new discovery adds a detail to our understanding, whether it is the precise composition of a vent plume, the role of microbial communities in altering chemical pathways, or the influence of physical forces such as turbulence and stratification on the dispersion of these plumes. These findings contribute to a broader narrative about the dynamic nature of the deep ocean and its critical role in Earth's overall environmental system. In summary, deep-sea chemical plumes are a remarkable and multifaceted phenomenon. They arise from the convergence of geochemical, biological, and physical processes under conditions of extreme pressure and near-freezing temperatures. Detected by advanced sensors and studied through a combination of field observations and laboratory experiments, these plumes offer a window into the hidden dynamics of the ocean's interior. Their study is essential for understanding deep ocean circulation, the global carbon cycle, and the unique ecosystems that rely on chemosynthetic energy. Though much remains to be discovered, the ongoing research promises to further illuminate the subtle and complex forces at work beneath the waves, a testament to the enduring mystery and beauty of our planet's final frontier. Abandoned submarine cables are among the ocean floor's most enduring relics, a silent archive of human communication history that has puzzled researchers for decades. These cables, originally laid to carry telegraph and telephone signals across vast oceans, now lie dormant beneath layers of sediment and marine growth, offering clues to both technological evolution and natural deep-sea processes. Many of these cables were installed in the 19th and early 20th centuries. As new technologies emerged and cables were replaced, vast networks of these once vital communication links were left behind. Over time, they have become subject to natural forces, corrosion from seawater, shifting sediments, and colonization by marine organisms. Although their primary purpose is long obsolete, the physical condition and distribution of abandoned cables remain an enigma. In some cases, cables that should have deteriorated have persisted remarkably well, while others have vanished without trace, leaving behind only faint sonar echoes. Studies show that the survival of these cables depends largely on the local environment. In areas where the seafloor is stable and relatively free of strong currents, cables can remain intact for many decades. Their robust outer sheaths, often made of lead, copper, or robust polymers, provide protection against corrosive saltwater and mechanical wear. However, in more dynamic regions, such as near mid-ocean ridges or in areas of high sediment transport, cables are more likely to be broken up by shifting seabed or even entirely buried under new layers of sediment. This uneven preservation creates a puzzle. Why do some cables remain surprisingly intact while others are lost or degraded beyond recognition? Modern deep-sea exploration has brought many of these abandoned cables back into focus. Remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, equipped with high-resolution cameras and advanced sonar mapping systems have documented numerous instances of old cables lying along the seafloor. In some regions, these cables form long, continuous lines stretching for hundreds of kilometers, while in other areas they appear only as isolated fragments. Detailed mapping has revealed that many cables, although abandoned, have become integrated into the seafloor environment. Over time, marine organisms colonize their surfaces, transforming them into artificial reefs that support diverse ecosystems. This biological colonization is not only of ecological interest, but also provides clues about the age and history of the cable. Layers of encrusting organisms and sediment can indicate how long a cable has been in place. The puzzle deepens when researchers consider the history and intended lifespans of these cables. Many were designed to function for only a few decades. However, some have persisted for well over a century. The surprising durability of these cables has led scientists to investigate the materials and construction methods used during early cable manufacturing. For instance, early transatlantic telegraph cables, which were among the first to be laid across the Atlantic Ocean, utilized complex engineering solutions to protect delicate copper cores from the corrosive ocean environment. These historical engineering feats, while innovative at the time, have left behind physical evidence that continues to defy easy explanation when compared to modern materials. The study of these cables thus offers a unique intersection between historical technology and contemporary marine science. Another aspect of the abandoned cable mystery is the question of their disappearance. While many cables remain visible on sonar images and in direct observations by ROVs, some expected cables are conspicuously absent from modern surveys. Various factors could explain these disappearances. In some cases, the cables may have been damaged by ship anchors, fishing nets, or even natural disasters like undersea landslides. Over long periods, the combination of corrosion, biological activity, and physical disturbances can cause a cable to break into fragments that are then dispersed by deep ocean currents. Once fragmented, the pieces may be too small to be easily detected, effectively erasing the cable from our modern maps of the seafloor. Advances in deep-sea sensor technology have improved our ability to detect these remnants, yet challenges remain. The deep ocean is an environment of low visibility and high pressure, where even the most advanced equipment must contend with a constantly shifting seafloor. Multi-beam sonar and magnetometer surveys have been instrumental in locating abandoned cables, but interpreting the resulting data is complex. The cables can be confused with natural features, such as sediment drifts or volcanic dikes, especially when they have been buried under sediment or overgrown with marine life. Researchers often combine multiple lines of evidence, from historical records and engineering blueprints to modern sensor data, to confirm the identity of a suspected cable. In several well-studied cases, scientists have recovered segments of abandoned cables for laboratory analysis. These studies reveal not only the composition of the cable materials, but also the effects of prolonged exposure to the deep ocean environment. For example, the oxidation state of copper and the corrosion patterns on metal sheaths can provide insights into the water chemistry, temperature fluctuations, and even the local sedimentation rates. In some cases, unexpected chemical signatures have been detected, such as unusual isotopic ratios or the presence of trace elements that were not part of the original manufacturing process. These findings raise further questions. Are these anomalies purely the result of natural degradation, or might they also reflect previously unknown chemical interactions on the seafloor? The ecological impact of abandoned submarine cables is another facet of this puzzle. As cables degrade and disintegrate, they release materials into the surrounding environment. The dissolved metals and polymers can become part of the sediment, potentially influencing local geochemical cycles. In some ecosystems, the cables have become substrates for bacterial colonies and even serve as attachment points for sessile invertebrates. Over time, these artificial structures can significantly alter the local habitat, providing new niches for marine life. Yet, while they may offer ecological benefits, they also pose potential risks, such as introducing pollutants or interfering with the natural dynamics of the seafloor. In terms of practical applications, understanding the fate of abandoned submarine cables is important for modern marine infrastructure. Today, submarine cables form the backbone of global telecommunications and the internet. As new cables are laid to replace aging ones, there is considerable interest in tracking the remnants of the old networks. The physical presence of abandoned cables can sometimes complicate new installations, particularly in areas with complex seafloor topography. Additionally, the environmental impact of these relics is an ongoing concern for regulatory agencies, which must balance the needs of modern communication infrastructure with the preservation of deep-sea ecosystems. Some researchers have proposed that abandoned cables might also serve as indicators of broader oceanographic processes. Because they are fixed to the seafloor, these cables can be used as reference points in studies of seafloor movement and sediment transport. By monitoring changes in the position or condition of a cable over time, scientists can infer the rates of seafloor deformation, the dynamics of underwater landslides, or the patterns of ocean current-induced erosion. This kind of long-term monitoring is challenging, but it offers the potential to reveal subtle changes in the deep ocean that might otherwise go unnoticed. The mystery of abandoned submarine cables is not only a story of technological relics, but also a window into the interaction between human history and natural processes. Each cable laid across the ocean is a testament to human ingenuity and the drive to connect distant lands through communication. Yet, once their operational lives end, these cables become part of the ocean's natural landscape, silent witnesses to the passage of time and the relentless forces of nature. Over decades and centuries, they are slowly worn away, reshaped, or even erased by the complex interplay of physical, chemical, and biological processes at work on the seafloor. Recent deep-sea expeditions have reinvigorated interest in this topic, as researchers use a combination of modern technology and historical research to map the vast network of abandoned cables. Archival records from the era of early submarine telegraphy and telephone systems are being cross-referenced with current sensor data to identify the routes of these cables and assess their current condition. In some instances, previously unknown segments have been discovered, shedding new light on the scale and complexity of early underwater communication networks. Furthermore, environmental studies are beginning to assess the role of these cables in deep-sea ecosystems. The colonization of cable surfaces by organisms, from simple bacteria and algae to more complex sessile invertebrates, provides an unexpected source of habitat in an otherwise featureless landscape. These micro-ecosystems can be quite diverse, offering insights into the adaptability of life in extreme environments. At the same time, understanding the degradation products of these cables, such as dissolved metals and plastics, is important for assessing their long-term impact on ocean chemistry and biology. While many of the mysteries surrounding abandoned submarine cables remain unsolved, the continued integration of historical records, field observations, and advanced analytical techniques promises to gradually unravel their secrets. Each piece of recovered cable material tells a story of the materials and methods used in its construction, of the environmental conditions it has endured, and of the gradual transformation that occurs when human technology is reclaimed by nature. The study of these relics not only enhances our understanding of deep-sea processes, but also bridges the gap between human technological history and the natural evolution of the ocean floor. In summary, the puzzle of abandoned submarine cables is a multifaceted one that touches on history, technology, and natural science. These cables, once vital links in global communication networks, now lie forgotten on the seafloor, slowly eroding and becoming part of the deep ocean landscape. Their survival, degradation, and occasional disappearance raise questions about the interactions between engineered materials and the relentless forces of nature. From the effects of corrosion and sedimentation to the biological colonization that transforms them into artificial reefs, each cable presents a unique case study in how human artifacts evolve over time in an environment as harsh as the deep ocean. As researchers continue to piece together the story of these abandoned cables, every new discovery contributes to a broader understanding of both past technological achievements and the ongoing natural processes that shape our planet. The integration of historical archives with cutting-edge deep-sea exploration techniques offers a promising path forward, one that may eventually reveal not only the fate of these cables, but also deeper insights into the dynamics of the ocean floor itself. The mystery endures, not as a call for dramatic conclusions, but as a rich and detailed chapter in the story of human innovation and nature's timeless, transformative power. Deep-sea sediment cores reveal an intricate record of our planet's history, yet within these layers, scientists have repeatedly encountered odd, periodic stratigraphic anomalies that remain a subject of intense debate. These unexpected layers, sometimes only a few millimeters thick yet distinct from the surrounding sediments, seem to disrupt what would otherwise be a smooth, gradual accumulation of material on the abyssal plain. The deep ocean is a remarkably slow depositional environment. Over millions of years, a continuous drizzle of fine particles, ranging from biogenic material such as the remains of microscopic plankton to terrigenous dust blown over from distant continents, settles on the seafloor. Under normal conditions, these sediments create a relatively uniform record of gradual change. However, in many drilling programs, including those conducted by the Ocean Drilling Program, ODP, and the Integrated Ocean Drilling Program, IODP, researchers have discovered layers that deviate markedly from the background. These anomalous layers can differ in color, grain size, chemical composition, and even fossil content, and they often occur at seemingly regular intervals, hinting at periodic processes that disrupted normal sedimentation. One well-known explanation for these stratigraphic anomalies involves episodic events such as volcanic eruptions. Volcanic ash, or tephra, can be ejected high into the atmosphere during explosive eruptions and then settle on the ocean surface, eventually becoming incorporated into the sediment record. These tephra layers are typically rich in silica and can be traced over large areas, serving as time markers that correlate with specific volcanic events. In many sediment cores, such ash layers appear as thin, sharply defined horizons that contrast with the more diffuse background sediment. However, not every anomaly fits the profile of a volcanic deposit. Some layers show a gradual change in composition or contain unusual concentrations of organic material, suggesting that other processes are at work. Climatic variations also offer a compelling explanation. Milankovitch cycles, the periodic changes in the Earth's orbit and tilt, profoundly influence global climate. These cycles modulate weather patterns, ocean circulation, and biological productivity, which in turn affect the rate and nature of sediment deposition. During periods of increased aridity, for example, higher amounts of dust are blown from continental interiors and deposited in the ocean, while wetter periods may result in enhanced biological productivity, leading to greater accumulation of biogenic material. The interplay between these cycles can produce rhythmic layers that stand out from the norm. Some anomalies have been linked to abrupt climate events, such as rapid warming or cooling episodes, which can leave distinct signatures in the form of unusual isotopic ratios or shifts in microfossil assemblages. Another potential cause of these sedimentary puzzles is related to ocean dynamics. Turbidity currents, underwater flows of sediment-laden water, can be triggered by submarine landslides, earthquakes, or even storms. When such a current sweeps over the seafloor, it can deposit a relatively thick, well-sorted layer of sediment known as a turbidite. Turbidites often display a characteristic graded bedding where the particle size decreases from the base to the top of the layer. In some regions, repeated turbidity current events can create a series of similar layers, which, if not clearly distinguished from the background, may appear as periodic anomalies. The challenge for scientists lies in differentiating these event layers from those produced by more continuous sedimentation processes. Some anomalies are even more enigmatic because they do not fit neatly into any of the well-established categories. In certain abyssal sediment cores, researchers have identified layers with unexpected mineralogical or chemical signatures. These might include unusual concentrations of trace elements like nickel, chromium, or rare earth elements that do not match the typical composition of the surrounding sediment. In some cases, these layers are enriched in organic carbon or exhibit distinct isotopic ratios that suggest a sudden influx of material from an external source. One hypothesis is that these layers could be the result of extraordinary events, such as a meteorite impact or a massive dust storm from a distant continent, which would inject an atypical mix of particles into the ocean. While such interpretations are still debated, they underscore the fact that the deep-sea sedimentary record is not simply a steady accumulation of material, but a dynamic archive that captures both gradual processes and abrupt, sometimes catastrophic events. The spatial distribution of these anomalous layers also raises intriguing questions. Some sediment cores from different ocean basins show remarkably similar periodic anomalies, suggesting a global-scale process influencing sedimentation. For instance, widespread dust deposition events, possibly linked to glacial-interglacial cycles or large-scale volcanic eruptions, might leave a synchronous signature in sediments across the world. Conversely, in other regions, the anomalies appear to be highly localized, reflecting unique local conditions such as specific tectonic settings or isolated sources of organic matter. This variability indicates that while some anomalies may be the result of universal climatic or astronomical cycles, others are controlled by regional geological factors. Modern techniques have advanced our ability to study these deep-sea sediment layers in exquisite detail. High-resolution X-ray diffraction, XRD, and scanning electron microscopy, SEM, are commonly used to analyze the mineralogy and microstructure of sediment layers. Isotopic analysis, particularly of oxygen and carbon isotopes, provides valuable information about past ocean temperatures and biological productivity. These methods allow scientists to reconstruct environmental conditions over millions of years, with some sediment cores offering an almost continuous record of Earth's climatic history. When periodic anomalies are identified, they can often be correlated with known events, such as major volcanic eruptions, rapid climate shifts, or even extraterrestrial impacts. However, many of these layers remain unexplained, continuing to fuel debates about their origin. Fieldwork plays a crucial role in this research. Deep-sea drilling programs retrieve sediment cores from abyssal plains and continental slopes, providing physical samples that can be analyzed in laboratories around the world. These cores often reveal a layered structure, with alternating bands of fine-grained clay, biogenic ooze, and coarser turbidite deposits. Within this stratigraphic record, the anomalous layers stand out because they do not follow the expected pattern of gradual change. In some cases, the anomalies are so pronounced that they are referred to as event beds or geochemical markers in the sedimentary record. Understanding the timing, duration, and composition of these layers is essential for piecing together the history of deep-sea processes. One intriguing case involves sediment cores recovered from the North Atlantic, where researchers identified a series of thin, dark layers interbedded with lighter, more uniform sediment. These dark layers are enriched in organic carbon and certain trace metals, suggesting that they might represent periods of high productivity or sudden influxes of terrestrial material. The timing of these layers, as determined by radiometric dating, appears to coincide with known climatic events, such as rapid warming periods or shifts in ocean circulation. Yet, some of the layers remain anomalous even when compared with global climatic records, leading to the possibility that they may represent localized events or even unknown processes. The mystery deepens when considering the role of bioturbation, the disturbance of sediments by the activities of living organisms. In many deep-sea environments, benthic organisms such as worms, crustaceans, and even fish disturb the sediment, mixing layers and blurring the stratigraphic record. Yet, in some cores, the anomalous layers are remarkably well preserved, with clear boundaries that suggest minimal biological disturbance. This raises questions about the conditions under which these layers were deposited. Perhaps the anomalies were formed during events so rapid that there was little time for bioturbation to occur. Alternatively, the sediment in those regions may be inherently less susceptible to disturbance, perhaps due to low oxygen levels or the presence of stabilizing minerals. Understanding these factors is key to unraveling the origins of the periodic anomalies. Another hypothesis for these odd patterns involves episodic changes in sedimentation rates. During certain periods, the rate at which sediment accumulates on the seafloor can change dramatically. These variations can result from shifts in ocean currents, changes in continental erosion rates, or even the influence of sea level fluctuations. For example, during glacial periods, lower sea levels may expose continental shelves to increased erosion, leading to higher rates of sediment deposition when sea levels rise again. Such episodic events could create distinct layers in the sediment that stand out against a backdrop of more constant accumulation. These layers, often enriched in specific minerals or organic compounds, may serve as natural time markers that record significant changes in Earth's environment. Technological advances have also improved our ability to analyze the composition and structure of deep-sea sediments. Laser ablation inductively coupled plasma mass spectrometry, LA-ICP-MS, allows for precise measurements of trace elements in sediment layers, revealing subtle shifts in geochemical composition that may be linked to external events. Combined with high-resolution imaging techniques, these methods provide a detailed view of the sedimentary record, allowing scientists to map the exact boundaries and internal structures of anomalous layers. This level of detail is crucial for testing various hypotheses about the origin of these anomalies, whether they are due to sudden influxes of material, changes in sedimentation dynamics, or alterations in the chemistry of the deep ocean. Interdisciplinary studies continue to refine our understanding of these deep-sea sediment anomalies. Geologists, oceanographers, and climate scientists collaborate to correlate sedimentary records with global climate models and tectonic histories. In some cases, the periodic anomalies in sediment layers have been linked to Milankovitch cycles, cyclic variations in Earth's orbit that influence climate on timescales of tens of thousands of years. These cycles can drive changes in continental weathering, ocean circulation, and biological productivity, all of which can be recorded in the sedimentary archive. However, not all anomalies fit neatly into this framework, and many remain a matter of debate. Some layers may record events that are localized in nature, such as submarine landslides or sporadic dust storms, while others might be the result of unknown or poorly understood processes. One striking aspect of these odd sediment patterns is their potential to serve as windows into past environmental conditions. Each anomalous layer is, in effect, a snapshot of the state of the ocean and the climate at the time of its formation. By studying these layers, scientists can infer changes in ocean temperature, nutrient availability, and even the frequency of extreme events such as volcanic eruptions or meteorite impacts. The sedimentary record thus provides a long-term archive of Earth's history, capturing both gradual trends and abrupt, episodic events. This archive is invaluable for reconstructing past climates and for understanding how the Earth system responds to various forcings, a critical area of research in the context of contemporary climate change. Field studies are essential in this research, and deep-sea drilling campaigns have retrieved cores from a variety of settings, from the abyssal plains of the Pacific to the continental slopes of the Atlantic. In these cores, the anomalous layers are often interbedded with more uniform sediment, creating a stratigraphic puzzle that researchers must piece together. The precise thickness, composition, and frequency of these layers vary widely from one location to another, suggesting that a range of processes may be responsible. Some regions exhibit periodic anomalies that recur at regular intervals, while in others the anomalies are sporadic with no apparent pattern. This diversity underscores the complexity of deep ocean sedimentation and the multitude of factors that can influence it. In many respects, the study of odd patterns in deep-sea sediment layers is a journey into the deep past, a way of reading the Earth's history written in layers of clay, silt, and organic matter. Each anomalous layer is a chapter in this story, offering clues to events that may have shaped the ocean's chemistry and the global climate. Whether it is a sudden influx of dust from a major volcanic eruption, a spike in biological productivity linked to climatic shifts, or a localized event such as a submarine landslide, these layers provide tangible evidence of processes that have long since passed. Yet, despite decades of study, many of these layers remain enigmatic, challenging scientists to develop new models and refine existing theories. The quest to understand these stratigraphic anomalies is ongoing, and new technologies continue to push the boundaries of what we can observe. Autonomous underwater vehicles equipped with high-resolution cameras and advanced sampling tools are now capable of retrieving sediment cores from previously inaccessible depths. These samples are then analyzed using state-of-the-art laboratory techniques, including LAICP-MS and X-ray diffraction, which allow for a detailed characterization of the chemical and mineralogical composition of each layer. The integration of these data with long-term monitoring and remote sensing techniques is gradually building a more comprehensive picture of how and why these odd sedimentary patterns form. In summary, the puzzle of odd patterns in deep-sea sediment layers is a multifaceted mystery that lies at the intersection of geology, chemistry, and climate science. These stratigraphic anomalies, whether resulting from episodic events, cyclical climate variations, or localized geological processes, challenge our understanding of deep ocean sedimentation. They serve as both a record of Earth's dynamic environmental history and a testament to the complex interplay of natural forces that continue to shape our planet's surface over geological time. As research advances, each new discovery in these sediment layers adds another piece to the intricate mosaic of Earth's history, offering insights into the processes that govern not only the deep ocean but also the broader Earth system. The study of these sedimentary puzzles is not merely an academic exercise. It has profound implications for our understanding of past climates, ocean circulation, and even the potential for future changes in Earth's environment. By unraveling the causes of these periodic anomalies, scientists hope to refine models of deep ocean processes, improve our understanding of the global carbon cycle, and better predict how the Earth might respond to future environmental changes. Each anomalous layer is a key to unlocking a part of this grand puzzle, a silent testimony to the power and complexity of natural processes that have been unfolding for millions of years. In the end, odd patterns in deep-sea sediment layers remind us that the ocean floor is a dynamic archive of Earth's history, a place where every grain of sediment carries a story, and every anomalous layer is a clue to the past. The mystery endures not because it defies explanation, but because it challenges us to look deeper and think more broadly about the forces that shape our world. In several deep-sea trenches, particularly in the Hadal Zone, researchers have recorded recurring acoustic echoes that defy easy explanation. These echoes, captured by arrays of hydrophones and long-term seafloor observatories, appear as distinct, rhythmic pulses that persist over extended periods. Unlike the transient sounds typically generated by marine life or by the normal creaking of sediment, these echoes have a steady, almost haunting quality that suggests they originate from processes not fully understood. One leading hypothesis is that these echoes result from the unique geometry of deep ocean trenches. The walls of these trenches are often steep and composed of hard, reflective rock. When sound waves, generated either by natural seismic events or by the slow shifting of sediment, hit these surfaces, they can reflect multiple times. In some cases, the architecture of the trench creates a resonant cavity. Within this cavity, acoustic energy can be trapped and gradually reverberate, producing echoes that recur with a consistent periodicity. The precise timing of these echoes appears to be linked to the dimensions and material properties of the trench walls, much like how sound reverberates within a cathedral. However, despite modeling these effects using principles of acoustic physics, researchers have found that the observed echoes sometimes exceed the expected duration and clarity of reflections based solely on trench geometry. Another potential contributor to these unexplained echoes is the presence of sediment layers with sharply contrasting acoustic properties. In many deep-sea environments, the seafloor is composed of layers that have been deposited over millennia. These layers can vary in density and composition, ranging from compacted clay to coarser sand or even volcanic ash. When sound waves travel through these heterogeneous layers, they can be partially reflected at each interface. Under certain conditions, the echoes produced at multiple boundaries can combine constructively, resulting in a series of distinct pulses that are recorded as recurring echoes. In some trench systems, scientists have noted that these echo patterns remain remarkably consistent over time, suggesting that the sediment layering is stable and that the interfaces act like natural acoustic reflectors. The behavior of underwater echoes is also influenced by the physical properties of the surrounding water. In the Hadal Zone, the near-freezing temperatures, high pressures, and relatively low levels of ambient noise create an environment where even weak acoustic signals can travel long distances. Sound propagation in water is affected by factors such as temperature gradients, salinity, and pressure, all of which are highly variable in deep trenches. For instance, a sudden change in temperature over a vertical distance can create a refractive effect, bending the path of sound waves and causing them to be focused or defocused. This phenomenon, known as acoustic lensing, may amplify echoes in some areas while diminishing them in others. In certain cases, the combination of reflective trench walls and refractive sound paths results in echo patterns that appear to repeat with uncanny regularity. Laboratory experiments have provided additional insights into the potential mechanisms behind these echoes. In controlled settings, scientists have recreated scaled-down models of trench-like environments using water tanks with adjustable temperature and salinity profiles. By placing sound sources at various positions within these tanks, researchers have been able to observe how acoustic signals reflect off artificial walls and pass through stratified layers of water. These experiments confirm that under the right conditions, a series of echoes can be produced that mimic the patterns observed in the field. However, the natural environment is far more complex than any laboratory model, and while the basic physics of sound reflection and refraction are well understood, the precise interplay of these factors in an actual deep-sea trench continues to present challenges. Seismic activity is another factor that may contribute to the phenomenon of unexplained underwater echoes. The deep ocean floor is a dynamic environment where even low-magnitude earthquakes occur with relative frequency. When a minor seismic event takes place, it can send a shockwave through the sediment. If the shockwave encounters a layer with markedly different acoustic impedance, it may be partially reflected, producing a detectable echo. In some instances, repeated micro-earthquakes, possibly associated with the gradual movement of tectonic plates, could generate a series of similar echoes over time. Although such events are typically recorded by seismometers as low-energy tremors, their cumulative effect on the acoustic environment may be significant enough to account for some of the recurring echo patterns. In addition to geological and physical factors, researchers have also considered biological influences on underwater echoes. The deep ocean hosts a wide range of biogenic structures, from large rigid shells and exoskeletons of deep-sea organisms to networks of microbial mats that can reflect sound. While it is unlikely that the regular periodic echoes are produced directly by marine life, the presence of such structures could alter the local acoustic properties. For instance, a dense layer of microbial biofilm on the seafloor might create an additional reflective interface, subtly modifying the echo pattern generated by natural geological features. Although these biological contributions are generally secondary, they add another layer of complexity to the overall phenomenon. Long-term monitoring of these echo patterns is a critical component of current research. Several deep ocean observatories have been deployed in regions known for recurring echoes, continuously recording data over periods that span months and even years. These long-term datasets allow scientists to examine how echo patterns vary with time and to correlate changes with other environmental factors, such as shifts in water temperature, sediment composition, or local seismic activity. In some observatories, researchers have noted that the echoes become slightly more pronounced during periods of increased tectonic activity or following episodic venting events. This correlation suggests that the echoes may serve as a natural barometer for deep-sea processes, providing indirect information about the state of the sea floor. Advanced computational models are now being employed to simulate the acoustic environment in deep trenches. By integrating data from field observations, laboratory experiments, and long-term monitoring, scientists are developing models that capture the interplay of reflective surfaces, refractive effects, and transient seismic events. These models help to predict how acoustic signals should behave under a range of conditions and allow researchers to test various hypotheses regarding the origin of the unexplained echoes. Although these models have provided valuable insights, they are still being refined to account for the inherent variability and complexity of the deep ocean. One particular area of interest is the role of trench geometry. Deep-sea trenches are not uniform. They often feature complex topographies with multiple slopes, ridges, and depressions. In some cases, the trench itself can act as a natural waveguide, channeling sound along its length. This phenomenon, combined with the reflective properties of the trench walls, may give rise to echoes that persist over surprisingly long distances. Detailed sonar mapping of these trenches has revealed that even slight variations in the angle or curvature of the walls can have a dramatic effect on the echo patterns. In some regions, the echoes form a regular, repeating pattern that seems to be dictated by the precise dimensions of the trench, a kind of natural acoustic fingerprint. Isolating the specific sources of these echoes remains a significant challenge. The deep ocean is a noisy place, despite the relative absence of human activity. Background noise from distant seismic events, the hum of the Earth's magnetic field, and even the subtle movements of deep-sea creatures all contribute to an acoustic environment that is rich in overlapping signals. To extract the echoes of interest, scientists use sophisticated signal processing techniques. By analyzing the frequency spectra and time intervals of the recorded sounds, researchers can identify patterns that are distinct from the ambient noise. In some cases, these analyses have revealed echo patterns that recur with remarkable regularity, suggesting that they are produced by stable, persistent features of the seafloor. The potential applications of understanding these unexplained underwater echoes are significant. For one, they could provide valuable insights into the processes that govern deep-sea dynamics. Since the echoes are influenced by both the physical structure of the seafloor and the properties of the overlying water, they could serve as natural indicators of changes in deep ocean conditions. For example, a sudden alteration in the echo pattern might signal a shift in sediment deposition, a change in fluid flow, or even the onset of a seismic event. Such information could be vital for deep-sea exploration, resource extraction, and even for understanding broader environmental changes that impact the global ocean. Moreover, these echoes might also play a role in the study of deep-sea ecosystems. The deep ocean is home to a variety of organisms that have adapted to life in complete darkness and under extreme pressure. The way these organisms interact with the physical environment, including how they navigate using acoustic cues, is still not fully understood. Unexplained echoes may provide additional data on how sound propagates in the deep sea, which in turn can shed light on how deep-sea creatures communicate and orient themselves. This is an active area of research, and ongoing studies continue to explore the ecological implications of deep ocean acoustics. In summary, unexplained underwater echoes in deep-sea trenches present a compelling puzzle that bridges the realms of geology, physics, and marine biology. These echoes arise from a complex interplay of factors, including the reflective geometry of trench walls, the heterogeneous nature of seafloor sediments, and the dynamic processes of fluid flow and seismic activity. Advanced observational techniques, such as long-term monitoring with hydrophones, high-resolution sonar mapping, and in situ chemical analysis, are gradually uncovering the patterns and causes of these mysterious acoustic signals. While many questions remain, the current evidence suggests that these echoes are a natural product of the deep ocean's dynamic environment, offering a subtle yet profound glimpse into processes that operate far below the surface. The study of these echoes is a testament to the power of modern oceanographic research, blending historical methods with cutting-edge technology to explore one of Earth's final frontiers. As researchers continue to refine their models and gather more data, each new discovery brings us closer to a full understanding of the factors that shape these persistent acoustic signatures. Though they are invisible to the naked eye, these underwater echoes resonate as clear reminders of the ongoing, relentless activity that defines the deep ocean. Every pulse, every recurrent sound recorded in these trenches is a piece of the larger narrative of Earth's interior dynamics. They reflect the fundamental principles of physics, sound propagation, reflection, refraction, and resonance, operating in an environment where the normal rules of life seem to be suspended. In the silent depths, where light is scarce and the pressure immense, these echoes serve as the only audible record of the vast, mysterious processes unfolding below. By continuing to study and analyze these acoustic phenomena, scientists are not only advancing our understanding of deep-sea dynamics, but also opening new windows into the Earth's geophysical processes. The recurring echoes provide critical clues to the structure and composition of the seafloor, the movement of sediments, and the influence of tectonic and hydrothermal activity on the deep ocean. As technology improves and long-term datasets expand, the potential to decode these echoes will only grow, offering the promise of insights that could reshape our understanding of the deep ocean. In this ongoing quest, every observation, every carefully measured pulse of sound, is a step toward unveiling the secrets of the abyss. The deep ocean remains a realm of quiet mysteries where the boundaries between the known and the unknown are constantly redrawn by natural processes that have been at work for eons. Unexplained underwater echoes are one of those enduring mysteries, a subtle, persistent song from the depths that continues to captivate the scientific community and challenge our perceptions of the natural world. The echoes may be faint and their origins complex, but they are undeniably real, a natural symphony composed by the forces of the earth, recorded by the tools of modern science, and slowly revealing the hidden dynamics of one of our planet's most extreme environments. Deep beneath the sunlit surface, in the crushing darkness of the abyss, there are regions where the seafloor is not simply a static expanse of sediment and rock, but rather a dynamic theater of suspended formations that drift like clouds. These enigmatic deep-sea clouds have been observed on sonar and through remotely operated vehicles, ROVs, appearing as diffuse, irregular plumes that hang suspended in the water column. Their ethereal appearance has sparked considerable debate among scientists. Are these clouds merely suspensions of organic or inorganic material, or do they represent an unknown physical process at work in one of Earth's most extreme environments? One of the primary theories is that these cloud-like formations are suspensions of biological material. In many deep-sea regions, the primary productivity is driven not by sunlight but by chemosynthetic bacteria that thrive around hydrothermal vents and cold seeps. These microorganisms convert inorganic compounds, such as hydrogen sulfide and methane, into organic matter. Over time, significant amounts of this biogenic material can accumulate and become entrained in the water column. In the darkness of the deep ocean, with very little turbulence to quickly disperse them, these biological particulates can form diffuse clouds that appear on acoustic and optical sensors. Analyses of water samples collected near these formations have revealed elevated concentrations of organic carbon and cellular fragments, supporting the hypothesis that at least some of the deep-sea clouds are biological in origin. Alternatively, some researchers argue that the clouds may be the product of purely physical processes. In the deep ocean, where pressure is immense and temperatures are near freezing, even minor fluctuations in water chemistry or sedimentation rates can lead to dramatic changes in how materials aggregate. One possibility is that these clouds are composed of fine mineral particles, such as clay, iron oxides, or other detritus, that are lifted from the seafloor by slow, persistent currents. Over time, these particles can form a colloidal suspension that resembles a cloud. Laboratory experiments have shown that under high-pressure conditions, similar to those found in the deep ocean, mineral particles can aggregate in a manner that is influenced by factors such as pH, salinity, and the presence of organic binding agents. The resulting structure, while ephemeral, can be extensive enough to be detected by modern sonar systems. A third hypothesis proposes that these enigmatic clouds may arise from a combination of biological and physical processes. In many deep-sea environments, the interplay between organic matter and mineral particles is intricate. For example, bacteria can produce extracellular polymeric substances, sticky, gel-like compounds that help cells adhere to surfaces. These polymers can bind mineral particles together, enhancing their tendency to remain suspended in the water column. In such a scenario, the deep-sea cloud would be a hybrid formation, partly biological, partly mineral, and maintained by both the inherent buoyancy of the suspended materials and the slow, steady currents that permeate the abyss. Field observations have played a crucial role in documenting these phenomena. During several deep-sea expeditions, ROVs have recorded video footage showing large, diffuse patches that drift lazily through the water. In some instances, the clouds have been observed near seafloor features such as submarine canyons, hydrothermal vent fields, or areas of active sediment resuspension. The shape and density of these clouds can vary widely. Some appear as thin, wispy veils, while others are more compact and opaque, obscuring parts of the seafloor beneath. These differences likely reflect variations in the source and composition of the material as well as the local hydrodynamic conditions. Advanced instrumentation has allowed researchers to measure the optical and acoustic properties of the clouds. High-resolution sonar mapping often reveals that the clouds have a diffuse, sometimes fuzzy appearance, indicating a complex internal structure. Optical sensors can detect the subtle scattering of light by the suspended particles, although the deep-sea darkness means that these observations are often limited to the few moments when artificial lighting is available. Chemical sensors, meanwhile, have provided data on the concentration of dissolved organic and inorganic compounds within these clouds, offering clues about their origin. In some cases, the chemical signature indicates a high level of biological activity, while in others, the data suggest a more mineral-based composition. One interesting aspect of these deep-sea clouds is their temporal variability. Some clouds appear to be relatively stable, persisting for days or even weeks in a given location, while others are transient, forming and dissipating over the course of hours. This variability may be linked to episodic events such as submarine landslides or localized releases of methane from gas hydrates. When a landslide occurs, fine particles are suddenly lifted into the water column, forming a temporary cloud that slowly settles back to the seafloor. Similarly, the rapid dissociation of gas hydrates can inject both gas and fine sediment into the surrounding water, creating a transient, cloud-like formation. Monitoring these events over time has allowed scientists to correlate the appearance of deep-sea clouds with specific geological or environmental triggers, although many instances remain unexplained. The study of these formations is not only of academic interest, it also has practical implications. Deep-sea clouds can affect the local biogeochemistry by altering the distribution of nutrients and influencing the rates of chemical reactions in the water column. For example, if a cloud is particularly rich in organic matter, it may fuel bacterial growth, which in turn can impact the oxygen levels in the surrounding water. This has consequences for the deep-sea ecosystems that rely on a delicate balance of nutrients and oxygen. Moreover, understanding these clouds is important for interpreting sonar data and for improving our models of deep ocean circulation. both of which have broader implications for climate studies and for the assessment of deep-sea resources. Interdisciplinary research is at the heart of this investigation. Oceanographers, geochemists, biologists, and physicists work together to unravel the complex interplay of factors that give rise to these enigmatic clouds. Fieldwork combined with laboratory experiments has allowed researchers to simulate deep-sea conditions and observe how different materials behave when suspended in water at high pressure and low temperature. These experiments have demonstrated that the aggregation of particles, whether biological, mineral, or a mixture of both, can lead to the formation of diffuse, cloud-like structures under the right conditions. Advanced modeling techniques are also being used to simulate the dynamics of these clouds, incorporating variables such as particle size, water density, and the intensity of local currents. One promising line of inquiry involves the use of long-term deep ocean observatories. By continuously monitoring a specific area over extended periods, scientists are able to capture the formation, evolution, and eventual dissipation of these clouds. Such observatories are equipped with a suite of sensors, including acoustic devices, optical cameras, and chemical analyzers, which work in tandem to provide a comprehensive picture of the phenomenon. Data collected from these observatories have revealed that some deep-sea clouds are correlated with specific environmental conditions, such as shifts in water temperature or sudden increases in sediment resuspension. This, in turn, provides critical insights into the underlying mechanisms that drive their formation. While much progress has been made, many questions remain. For example, the precise chemical pathways that lead to the formation of these clouds are still under investigation. In some instances, the clouds show a distinct enrichment in certain trace elements or organic compounds, which may be indicative of specific biological processes or unique geochemical reactions. Additionally, the physical dynamics of how these clouds are maintained, how the interplay between buoyancy, water currents, and particle aggregation prevents them from rapidly settling to the seafloor, is an area of active research. The behavior of these clouds, particularly in the context of deep ocean turbulence and stratification, remains a subject of intense study. Furthermore, the spatial distribution of deep-sea clouds is another intriguing puzzle. These formations are not uniformly distributed across the seafloor. Rather, they tend to occur in patches, often near features like submarine canyons or near active vent fields. This spatial variability suggests that localized environmental conditions play a significant role in their formation. In areas where deep ocean currents are particularly strong or where the sediment is easily resuspended, the conditions may be just right for the formation of a persistent cloud. Conversely, in regions where the seafloor is more stable and the water is less turbulent, such clouds may be rare or absent. The potential impact of these deep-sea clouds extends beyond academic interest. For instance, the presence of large, dense clouds of suspended particles can have significant effects on the propagation of sound in the ocean. This has implications for submarine communication and for the operation of sonar systems used by both the military and scientific communities. Changes in the acoustic properties of the water caused by these clouds can lead to signal attenuation or distortion, affecting everything from deep-sea navigation to the detection of marine life. Understanding these effects is crucial for improving the design of acoustic sensors and for developing more accurate models of deep ocean sound propagation. In summary, enigmatic deep-sea clouds represent one of the many mysteries of the deep ocean, a phenomenon that sits at the intersection of biology, chemistry, and physics. These cloud-like formations, observed as diffuse, drifting plumes in the abyss, may be composed of suspensions of biological material, mineral particles, or a complex mixture of both. Their formation appears to be driven by a combination of processes, including the resuspension of sediments, biological productivity near hydrothermal vents, and unique geochemical reactions that occur under high-pressure, low-temperature conditions. Advanced field observations using ROVs and long-term deep ocean observatories, combined with laboratory experiments and computational modeling, are gradually unraveling the processes that give rise to these mysterious clouds. The investigation into these formations is ongoing, and while many details remain unresolved, each new observation adds to our understanding of the deep ocean environment. The interplay of natural forces that create and sustain these clouds is a testament to the dynamic and ever-changing nature of the deep ocean, a realm where even the most subtle phenomena can have far-reaching implications for marine ecosystems, global climate, and our understanding of Earth's geophysical processes. Every deep-sea cloud is a clue, a small but significant piece of the puzzle that records the history and ongoing dynamics of our planet's most remote and mysterious environment. As researchers continue to refine their techniques and expand their observational networks, the hope is that the enigmatic nature of these deep-sea clouds will gradually give way to a clearer, more comprehensive understanding of the natural processes that govern the abyss. Deep beneath the crushing weight of the ocean, where darkness reigns and pressures exceed 1,000 times that at the surface, there is a mystery that has long troubled deep-sea explorers: the vanishing of deep-sea submersibles. One of the most widely discussed cases involves a remarkable unmanned vehicle known as Nereus. Designed to venture to the very limits of the ocean, Nereus was built to explore depths that few human-made machines could ever hope to reach. In its prime, it descended to depths exceeding 8,000 meters, enduring pressures that would flatten even the sturdiest structures. Yet in May 2014, while on an expedition in the remote Kermadec Trench of the South Pacific, Nereus simply vanished from all contact, leaving behind an eerie silence that has persisted ever since. Nereus was not just any submersible, it was a technological marvel, a hybrid remotely operated vehicle capable of operating autonomously. With a titanium pressure hull and state-of-the-art sensors, it was designed to navigate the inky abyss and send back detailed images and data of the seafloor. Its mission was to capture the mysteries of the deep and shed light on processes that take place in an environment so extreme that it seems almost alien. Yet, on that fateful day in May, its last transmissions were brief and erratic, and then they stopped altogether. Despite numerous search efforts using sophisticated sonar mapping and deep-sea ROVs, no trace of Nereus was ever found, and the cause of its disappearance remains an unresolved puzzle. The mystery of Nereus highlights the inherent dangers of deep-sea exploration. At depths where water pressures can exceed 1,000 atmospheres, even the smallest structural flaw or material fatigue can lead to catastrophic failure. The engineering behind these submersibles is extraordinary, yet the deep ocean is an unforgiving environment where conditions change rapidly. Temperature gradients can be steep, and chemical reactions under such extreme pressure may cause corrosion or embrittlement of materials over time. In the case of Nereus, some experts have speculated that a minor crack, possibly initiated during an earlier dive, might have expanded under the immense pressure, eventually leading to an implosion that would have left the vehicle in tiny fragments too scattered to be easily detected. Another possible factor is the challenge of maintaining reliable communication in such a hostile environment. Submersibles rely on acoustic signals to transmit data and position information to surface vessels. However, the deep ocean is filled with a cacophony of natural sounds, from the low rumble of tectonic movements to the clicking and murmuring of deep-sea life. In addition, the acoustic properties of water change with depth, temperature, and salinity, which can distort signals and sometimes cause a submersible to lose contact entirely. When a vehicle like Nereus goes silent, it leaves behind a void of information that only deepens the mystery, as the faint echoes of its last moments are often lost in the ocean's overwhelming din. Nereus is not the only submersible to have met such an ambiguous fate. There have been other instances over the decades where smaller, sometimes experimental, vehicles have disappeared during deep-sea operations. In many cases, these losses are shrouded in secrecy, as the challenges of operating in the abyss mean that even well-funded research programs sometimes experience unexplained failures. Some submersibles built decades ago with now outdated technology have also been lost, their remnants scattered over vast areas of the seafloor. The difficulty of locating and recovering wreckage in the deep ocean is immense. Even if a submersible does implode or crash, the resulting debris may be so widely dispersed by ocean currents that it becomes nearly impossible to piece together the chain of events. The loss of a deep-sea submersible is not only a technological and scientific setback, it is also a somber reminder of the limits of human exploration. Every time one of these vehicles disappears, it leaves behind not only unanswered questions about the fate of the machine and its crew, if manned, but also a gap in our understanding of the deep. These incidents force researchers to re-examine every aspect of submersible design, from the choice of materials and the architecture of pressure hulls to the reliability of communication systems and the protocols for emergency recovery. In some cases, the investigations have led to improvements in safety standards, while in others they have merely underscored the fact that the deep ocean remains one of the most challenging frontiers on Earth. In the case of Nereus, Extensive investigations by the Woods Hole Oceanographic Institution and independent researchers have combed through every available datum, acoustic logs, sensor readings, and eyewitness reports from other vessels in the region. One of the critical aspects under scrutiny is the behavior of the submersible's titanium hull under prolonged exposure to extreme pressures. Although titanium is renowned for its strength and resistance to corrosion, the cyclic loading and high stress at abyssal depths can eventually lead to fatigue failure. Computer simulations and material stress tests conducted after Nereus's disappearance have sought to replicate the conditions it experienced during its final dive. These experiments indicate that even minor imperfections in the hull, if not detected and corrected, can act as stress concentrators. Over time, these areas may develop cracks that grow steadily until the integrity of the entire structure is compromised. However, the precise moment of failure is unpredictable, and once the hull gives way, the implosion is so rapid and violent that any fragments are quickly reduced to minute particles. Some scientists have also pointed to the potential role of collisions with small, unseen obstacles on the seafloor. The ocean floor is not a flat, featureless expanse, but a rugged landscape dotted with rocky outcrops, sedimentary mounds, and even remnants of ancient volcanic activity. A submersible descending at extreme speeds, even if controlled, might encounter a protruding rock or an unexpected ridge that it is not designed to withstand. The impact, even if minor in the grand scheme, could initiate a chain reaction leading to structural failure. Yet, in the case of Nereus, no such impact was recorded by nearby sensors, leaving the collision theory as one of several unproven possibilities. Another challenge is the inherent difficulty of deep-sea recovery operations. The disappearance of a submersible in the deep ocean often means that its wreckage is scattered over an area that can be vast compared to the size of the vehicle. Ocean currents, the dynamic seafloor environment, and even bioturbation by deep-sea organisms can all contribute to the dispersion of debris. In the case of Nereus, search teams use high-resolution sonar mapping and autonomous underwater vehicles to scan the seafloor in the expected impact zone. Despite these efforts, no conclusive evidence of the submersible was found, suggesting that if it did break apart, the debris was either too small or too widely dispersed to be detected with current technology. One of the most chilling aspects of vanishing submersibles like Nereus is the silence that follows their disappearance. With no warning, no distress call, and no visible signs of a catastrophic event, the deep ocean swallows the vehicle whole, leaving only a gap in the data and a lingering sense of uncertainty. This silence is compounded by the fact that deep-sea expeditions are expensive and time-consuming. When a submersible vanishes, it not only represents a loss of a valuable research tool, but also a setback for the broader scientific community that depends on these missions to unlock the secrets of the abyss. In more recent times, the tragic loss of the Titan submersible, though not a vanishing case in the traditional sense, as its wreckage was eventually found, has brought renewed attention to the perils of deep-sea exploration. The Titan, operated by OceanGate, encountered catastrophic failure during a descent, leading to a loss of communication and ultimately a fatal implosion. While the Titan's fate was widely publicized and its wreckage located, it shares with Nereus the common thread of the deep ocean's unforgiving nature. These incidents serve as stark reminders that even the most advanced engineering and rigorous safety protocols cannot fully mitigate the inherent risks posed by the extreme conditions found thousands of meters below the surface. The scientific community continues to learn from each incident. For every vanishing submersible, extensive reviews are conducted to understand what went wrong. Material scientists, structural engineers, and oceanographers work together to improve designs, test new materials, and refine operational procedures. These collaborative efforts are essential, as the deep ocean remains one of the least understood and most difficult environments to explore. The lessons learned from past losses not only enhance the safety of future missions, but also push the boundaries of our technological capabilities, enabling deeper, more comprehensive studies of the Earth's final frontier. In addition to technical investigations, there is also a human element to these tragedies. The crews and researchers who dedicate their lives to deep-sea exploration often speak with a mix of awe and humility when describing their encounters with the abyss. The disappearance of a submersible like Nereus is not just a technical failure, it is a profound loss for the scientific community. Every lost mission is a reminder of the limits of our current understanding and the daunting challenges that lie ahead. It is a call to approach the deep with both ambition and respect, knowing that the ocean, in all its vastness and mystery, holds both extraordinary beauty and immense danger. Looking ahead, the ongoing development of new technologies offers hope for preventing future losses. Advances in materials science, such as the use of ultra-high-strength composites and improved metal alloys, aim to create pressure hulls that can withstand even greater stresses. Similarly, improvements in sensor technology and communication systems are enhancing the ability of submersibles to maintain contact with surface vessels, even in the most extreme conditions. Autonomous underwater vehicles are becoming more sophisticated, with longer endurance and better navigational capabilities, which may one day allow for more reliable tracking and recovery of submersibles that encounter trouble. Moreover, the lessons learned from the vanishing of deep-sea submersibles are inspiring innovations in rescue operations. Researchers are developing new methods to deploy rapid response recovery systems in the deep ocean. These systems, which include advanced sonar arrays and remotely operated recovery vehicles, are designed to locate and retrieve debris quickly, even if it is scattered over a wide area. The hope is that by reducing the time between a submersible's disappearance and the commencement of search efforts, more information can be gathered about the event, potentially preventing future tragedies and preserving valuable scientific data. The mystery of vanishing deep-sea submersibles is a testament to the extreme challenges of exploring one of Earth's final frontiers. The disappearance of Nereus, in particular, has become a symbol of the delicate balance between human ingenuity and the immense, unpredictable forces of nature. It is a reminder that the deep ocean is a realm of both wonder and peril, where every dive carries with it the risk of encountering the unknown. Yet, it is precisely this uncertainty that drives scientists to push the boundaries of exploration, to innovate, and to learn more about our planet's hidden depths. As researchers continue to piece together the puzzle of these lost vehicles, each new discovery contributes to a deeper understanding of the deep ocean. The data collected from acoustic sensors, pressure gauges, and material analyses are gradually revealing the subtle interactions of physical, chemical, and biological processes that govern the behavior of submersibles in the abyss. Every experiment, every simulation, brings us a little closer to knowing the truth behind these enigmatic vanishings. In the silent darkness below, where light is a rare visitor and every sound is magnified, the deep ocean holds its secrets close. The vanishing of submersibles like Nereus is a powerful reminder that despite all our advancements, there are still realms of the Earth where nature's might far exceeds our capacity to control or predict. It is a realm that demands both caution and curiosity, a place where the pursuit of knowledge must be tempered with respect for the forces that have shaped our world over eons. In the end, the mystery of vanishing deep-sea submersibles is not merely a tale of technological failure or engineering oversight. It is a window into the challenges of exploring a world that is as beautiful as it is brutal, a reminder that the deep ocean, with its unyielding darkness and crushing pressures, remains one of the most formidable environments on Earth. And in that unyielding darkness, every lost submersible whispers a quiet lesson, that the quest for knowledge is a journey into realms where certainty is elusive, and every answer only leads to further questions. Deep beneath the ocean's surface, near vast fields of hydrothermal vents, scientists have detected unusual, unexplained acoustic signals that seem to defy conventional expectations. In these dark, high-pressure environments where superheated water escapes from the Earth's crust into near-freezing seawater, a complex symphony of sound emerges, one that is both soothing and puzzling. Hydrothermal vents, which form at the boundaries of tectonic plates and along mid-ocean ridges, eject mineral-rich water at temperatures that can exceed 350 degrees Celsius. As this scalding fluid meets the frigid ambient water, it creates turbulent mixing zones where rapid temperature and pressure changes drive a host of physical and chemical processes. Among the many phenomena recorded in these vent fields are distinct acoustic anomalies. Researchers deploying arrays of hydrophones, underwater microphones sensitive to a broad range of frequencies, have noted that the sounds emanating from some vent sites are not merely the background rumble of shifting tectonic plates or the general hum of deep-sea life. Instead, these signals sometimes take on a rhythmic, almost musical quality, punctuated by sharp bursts of sound or low-frequency pulses that are out of step with typical ambient noise. One explanation for these anomalies lies in the dynamic behavior of bubbles in the vent plumes. When the superheated mineral-laden water is released, it contains dissolved gases that rapidly come out of solution as the water cools. These gases form bubbles that, under the crushing weight of the overlying water, oscillate and collapse in a phenomenon known as cavitation. The rapid formation, expansion, and implosion of bubbles can generate shock waves that produce distinct acoustic signatures. These sounds, sometimes described as a series of clicks or a low, rumbling boom, have been recorded by instruments deployed near active vent systems. The precise frequency and amplitude of these sounds depend on the size of the bubbles, the rate at which they form, and the properties of the surrounding water. In some vent fields, scientists have observed periodic pulses of sound that seem to correlate with the natural cycling of vent activity. As the intensity of the venting fluctuates, so too does the volume and rate of bubble formation. In moments when the vent activity intensifies, possibly due to changes in the underlying magma supply or shifts in the local tectonic stresses, the acoustic signals can become stronger and more defined. Conversely, during quieter periods, the sounds may fade into a soft, almost imperceptible hum. These temporal variations provide valuable clues about the complex interplay between geological and chemical processes occurring at the vent. Beyond bubble dynamics, another possible source of acoustic anomalies near hydrothermal vents is the resonance of vent structures themselves. The mineral deposits and chimneys formed by decades or even centuries of vent activity often build into towering columnar structures that extend from the seafloor. These structures, composed of sulfide minerals, iron oxides, and other precipitates, can act as natural resonators. When water flows past or through these porous, brittle formations, vibrations can be induced that amplify certain frequencies. In effect, the vent structures might sing in response to the kinetic energy of the circulating currents. This resonant effect has been compared to the way wind passing over a canyon or through a narrow passage can produce musical tones. In controlled laboratory experiments, researchers have attempted to mimic these natural processes. By recreating the conditions of rapid fluid mixing and bubble formation under high pressure, scientists have generated acoustic signals that closely match those recorded in the field. These experiments typically involve heating a mineral-rich solution to high temperatures and then rapidly cooling it under simulated deep-sea pressures. As the solution cools, tiny bubbles form and oscillate, producing sound waves that are captured by sensitive microphones. Although the laboratory settings can reproduce the basic physics of bubble dynamics and resonant vibrations, the natural environment of a hydrothermal vent is far more complex. Factors such as the heterogeneity of the seafloor, variable vent geometries, and the presence of biological communities all contribute to the rich tapestry of acoustic phenomena observed in the field. Another intriguing aspect of these acoustic anomalies is their potential role in monitoring vent activity and even broader geological events. Because the sounds produced by hydrothermal vents are so intimately connected to the processes occurring deep within the Earth's crust, they can serve as indirect indicators of tectonic or volcanic activity. For instance, a sudden change in the acoustic signature at a vent site might signal an impending change in the vent's output, perhaps due to a shift in the underlying magma chamber. Over time, long-term acoustic monitoring has the potential to reveal patterns in vent activity that could improve our understanding of deep Earth processes and even aid in the early detection of volcanic eruptions on the seafloor. Despite the progress made in characterizing these acoustic anomalies, many questions remain unanswered. One of the central challenges is distinguishing the acoustic signals generated by the venting process from other natural noises in the deep ocean. The deep-sea soundscape is filled with a variety of sources: the distant rumble of earthquakes, the subtle crackling of shifting sediments, and even the calls of deep-sea animals such as shrimp and fish. Advanced signal processing techniques are required to isolate the vent-specific sounds from this cacophony. Researchers employ spectral analysis and time series analysis to identify the frequency bands and temporal patterns that are unique to vent-generated sounds. These analyses have revealed that some acoustic anomalies have a surprisingly narrow frequency range, suggesting a controlled, almost harmonic process at work. Temperature gradients also play a crucial role in the generation of these sounds. The extreme contrast between the superheated vent fluid and the near-freezing surrounding water create steep thermal gradients that drive vigorous convection currents. These currents can, in turn, set up oscillatory flows that contribute to the production of sound. In some cases, the interplay between thermal convection and bubble dynamics leads to the emergence of complex acoustic patterns that are difficult to predict with existing models. Such complexity is a reminder of how little is known about the physical behavior of fluids under extreme conditions. There is also a possibility that biological factors influence the acoustic environment around hydrothermal vents. Although the primary sounds are clearly associated with physical and chemical processes, the deep-sea ecosystem is teeming with life. Tube worms, vent crabs, and specialized bacteria thrive in these hostile conditions, and their activities may modulate the acoustic signals. For example, some organisms may alter the local chemistry or produce biofilms on vent structures, subtly changing their resonant properties. While the biological contribution to the overall soundscape is likely secondary to the dominant physical processes, it adds another layer of complexity to the mystery. Ongoing research in this field involves interdisciplinary collaborations between oceanographers, geophysicists, chemists, and biologists. Large-scale ocean observatories equipped with networks of hydrophones and other sensors have been deployed in regions known for intense hydrothermal activity. These observatories provide continuous, long-term monitoring of the acoustic environment, allowing scientists to detect both gradual trends and sudden anomalies. Data collected over months and years are being analyzed using sophisticated computational models that simulate the dynamics of bubble formation, fluid flow, and structural resonance in vent systems. Such models aim to reproduce the observed acoustic spectra and to pinpoint the mechanisms responsible for specific anomalies. One fascinating outcome of this research is the potential to use acoustic signals as a window into the otherwise inaccessible depths of the Earth. In the dark, high-pressure environment of the deep ocean, sound travels long distances with little attenuation, making it an excellent tool for remote sensing. By correlating changes in acoustic signals with other geophysical data, such as temperature and chemical composition, researchers hope to build a comprehensive picture of the processes occurring at hydrothermal vents. This, in turn, could improve our understanding of not only deep-sea dynamics but also the fundamental interactions between the Earth's interior and its oceans. While the prevailing evidence supports a natural geophysical origin for these acoustic anomalies, the mystery remains open because of the inherent complexity of the deep ocean environment. The interplay between rapidly changing chemical conditions, extreme temperatures, and the unique physics of high-pressure fluids creates a scenario where even well-understood processes can produce unexpected results. Each new recording from a vent site adds another piece to the puzzle, revealing subtle variations in frequency, amplitude, and duration that challenge existing models. In summary, the acoustic anomalies observed near hydrothermal vents are a captivating mystery of the deep ocean. They arise from the dynamic interactions between superheated, mineral-rich fluids and the cold, dense seawater, with bubble dynamics, structural resonance, and possibly even biological processes all contributing to the sounds. While laboratory experiments have successfully replicated some of these phenomena under controlled conditions, the full complexity of the natural environment remains only partially understood. Sophisticated monitoring and advanced modeling techniques continue to shed light on these processes, yet many questions linger about the exact mechanisms and the variability of the signals across different vent fields. For now, the deep, dark waters around hydrothermal vents continue to sing their mysterious songs, a soothing yet enigmatic chorus that invites us to listen, ponder, and marvel at the natural wonders hidden beneath the ocean's surface. The gentle, rhythmic pulses of sound serve as a constant reminder of the extraordinary physical forces at work in our planet's most remote environments. As researchers refine their techniques and gather more data, each new acoustic recording brings us one step closer to unraveling the mystery of these underwater anomalies, deepening our understanding of the Earth's inner workings and the dynamic processes that shape our world. Deep-sea chemical pollution anomalies are among the most puzzling and intriguing findings in modern oceanography. In remote regions of the deep ocean, areas far removed from known sources of contamination, such as hydrothermal vents, river outflows, or industrial discharges, researchers have detected sudden, unexplained spikes in the concentrations of certain chemicals. These anomalies manifest as unexpected peaks in trace metals, organic compounds, or other chemical species in sediments or the overlying water column. Their presence challenges our understanding of deep ocean geochemical cycles and has prompted a re-examination of the processes that govern the long-term evolution of abyssal environments. Under normal circumstances, the deep ocean is characterized by a slow, steady deposition of sediment. Over millions of years, A constant drizzle of fine particles, including biogenic debris, dust, and mineral grains, settles on the seafloor, creating layers that record Earth's climatic and environmental history. This sedimentation process is usually gradual, resulting in relatively uniform layers with predictable chemical signatures. However, in some drilling programs and long-term monitoring projects, scientists have identified stratigraphic layers that deviate markedly from this background pattern. These anomalous layers often exhibit concentrations of trace elements or organic compounds that are significantly higher than those in surrounding sediments, and they do so without any immediately apparent natural or anthropogenic source. One of the more frequently observed anomalies involves unexpected spikes in certain trace metals, such as nickel, cobalt, or rare earth elements. In several deep-sea cores retrieved from abyssal plains in both the Atlantic and Pacific Oceans, researchers have found thin, discrete layers where the concentrations of these metals increase 2 to 3-fold relative to the background. Typically, such increases could be linked to volcanic ash deposits or hydrothermal inputs, yet in these cases, there is no associated evidence of volcanic activity or nearby vent fields. Instead, the anomalies are isolated in remote areas where sedimentation is expected to be relatively constant. One hypothesis is that these spikes represent episodic remobilization events, where ancient mineral deposits buried within the sediment are suddenly released into the water column. This could occur if subtle changes in the redox conditions or pH trigger the dissolution of previously stable minerals, causing them to be reprecipitated in a concentrated form. Another type of chemical anomaly involves the detection of unusual organic compounds in deep ocean water samples. While dissolved organic carbon is a common constituent of deep ocean waters, some measurements have revealed transient peaks in specific polycyclic aromatic hydrocarbons, PAH, or other complex organic molecules. PAHs are typically associated with combustion processes or oil spills. However, in these remote settings, there is no clear anthropogenic source. One possibility is that these compounds may derive from the diagenesis of ancient organic matter that has been locked away in the sediment for millennia. Under certain conditions, the slow breakdown of this material can release complex molecules in localized bursts. Alternatively, unknown microbial processes may be synthesizing these compounds as part of deep-sea biogeochemical cycles that are only beginning to be understood. Detection of these chemical anomalies relies on an array of sophisticated instruments. Conductivity temperature, depth, CTD, sensors, coupled with water samplers, provide a vertical profile of the ocean's physical and chemical properties. In addition, sediment cores are extracted by deep-sea drilling programs, and these cores are analyzed using techniques such as mass spectrometry, X-ray diffraction, and laser ablation inductively coupled plasma mass spectrometry, LAICP-MS. These methods allow researchers to determine the precise concentrations of elements and compounds in the sediments, and to construct a high-resolution timeline of chemical changes over millions of years. When a discrete anomalous layer is identified, scientists can compare its chemical fingerprint with known sources, such as volcanic ash, hydrothermal precipitates, or riverine inputs, to rule out conventional explanations. Interestingly, some anomalies appear to have a periodic nature, recurring at regular intervals in the sediment record. This rhythmic pattern has led some researchers to suggest that they might be linked to cyclical events, such as Milankovitch cycles, which drive long-term climatic variations. During periods of glacial advance or retreat, for example, the rate of dust deposition from continents can change dramatically, altering the chemical composition of the sediment. However, while some anomalous layers correlate with known climatic events, others do not, indicating that multiple, perhaps even overlapping, processes are responsible. One perplexing aspect of these anomalies is their occurrence in areas that are otherwise remarkably pristine. In the vast remote regions of the deep ocean, far from any significant human activity or natural sources of heavy metal input, the detection of elevated chemical concentrations is unexpected. In such settings, even low levels of chemical input should be well mixed and diluted by the slow but steady circulation of deep waters. The fact that anomalies persist in these regions suggests that they are not the result of recent pollution, nor are they simply a byproduct of natural sedimentation. Instead, they may be the signature of episodic events that release concentrated chemical inputs over short time frames, inputs that are then rapidly dispersed and later recorded in the sedimentary archive. There are several hypotheses regarding the origin of these unexplained anomalies. One possibility is that they result from the remobilization of ancient deposits. Over geological time, the seafloor acts as a vast repository for both natural and anthropogenic materials. In some cases, materials that were deposited millions of years ago may be reworked by shifting currents or episodic events, such as submarine landslides or earthquakes. This remobilization can concentrate certain elements in discrete layers, producing a chemical signal that appears anomalous when compared to the surrounding sediment. Another possibility is that localized, unknown geochemical reactions are at work, reactions that occur under the extreme pressure and temperature conditions of the deep ocean, and which may lead to the sudden precipitation of certain minerals. These reactions might be driven by factors such as microbial activity, changes in the availability of oxygen, or even interactions with underlying basaltic crust that are not yet fully understood. Anthropogenic contributions, though always a possibility in ocean studies, seem unlikely in many of these cases, given the remoteness of the affected areas. Modern pollution, whether from industrial discharges, shipping, or atmospheric deposition, is usually well documented and has distinct chemical markers. The anomalous layers in question, however, often lack these markers. For example, if an industrial spill were responsible, one would expect to find elevated levels of specific pollutants such as polycyclic aromatic hydrocarbons, PAHs, with a clear modern isotopic signature. Instead, the chemical composition of the anomalies often points to sources that are either ancient or natural in origin. This absence of modern contaminants strengthens the argument that the anomalies are not due to recent human activity. Field studies have also uncovered unexpected isotopic signatures within these anomalous layers. Isotopes of elements like carbon, oxygen, and iron are sensitive indicators of the conditions under which they were deposited. In some sediment cores, the ratios of these isotopes in the anomalous layers differ significantly from those in adjacent layers, suggesting a rapid or unusual change in the depositional environment. These isotopic shifts can sometimes be correlated with known events, such as volcanic eruptions or sudden climatic transitions, but in many cases they remain unexplained. The fact that these isotopic anomalies appear in isolated layers indicates that whatever process produced them was brief and localized, rather than part of a long-term, continuous process. Remote sensing technologies have further contributed to our understanding of deep-sea chemical anomalies. Multi-beam sonar, while primarily used for mapping the seafloor, can also detect variations in sediment density and composition that may be linked to chemical differences. In some deep ocean regions, areas with anomalous chemical concentrations appear as distinct patches or layers when viewed through these sonar images. Coupled with in situ chemical sensors, these observations have enabled scientists to create detailed maps of chemical variability on the seafloor, revealing patterns that were previously hidden. Recent international collaborations have focused on compiling and analyzing data from multiple deep-sea drilling programs and observatories. By comparing sediment cores from different ocean basins, researchers have identified recurring anomalies that seem to share a common signature, even though the regions are geographically disparate. This raises the possibility that these chemical anomalies may be linked to global-scale processes, such as changes in ocean circulation patterns or episodic events that have affected the entire planet. On the other hand, some anomalies appear to be unique to specific regions, indicating that local geological or environmental factors are at play. Despite significant progress, many challenges remain. The deep ocean is vast and inherently difficult to study, and many areas have been only sparsely sampled. The episodic nature of the anomalies means that they might be missed during a single expedition, requiring long-term monitoring and repeated sampling to capture their full variability. Moreover, while modern analytical techniques can detect and quantify minute concentrations of chemicals, interpreting these data in the context of complex deep ocean processes is an ongoing challenge. The interplay between physical, chemical, and biological factors in these remote environments is subtle, and developing a comprehensive model that accounts for all observed anomalies will require further research. The mystery of unexplained deep-sea chemical pollution anomalies, then, is not one of modern contamination, but rather a record of natural, episodic processes that have left their mark on the ocean's sedimentary archive. Whether the anomalies are the result of remobilized ancient deposits, sudden geochemical reactions, or brief episodes of enhanced sediment input, they offer a fascinating glimpse into the dynamic and often unpredictable nature of the deep ocean. Each anomalous layer in a sediment core is like a page from the Earth's history, a record of a moment when the usual balance of chemical inputs was disrupted, leaving behind a signature that defies simple explanation. In studying these anomalies, scientists are not merely cataloging unusual chemical spikes. They are piecing together a narrative of the deep ocean's evolution over millions of years. These chemical records provide insights into past climatic events, tectonic shifts, and even rare catastrophic episodes that have reshaped the seafloor. By analyzing the chemical and isotopic composition of these layers, researchers can reconstruct a timeline of environmental changes, offering a window into periods of intense volcanic activity, shifts in ocean chemistry, and other transformative events. The research is inherently interdisciplinary. Geochemists, oceanographers, paleoclimatologists, and geologists work together to interpret the data from sediment cores, remote sensing, and in situ measurements. This collaborative approach is essential because the anomalies often lie at the intersection of multiple processes. For example, an unusual spike in trace metals might be associated with a transient volcanic episode that also produced a distinct isotopic signature in the surrounding carbonate sediment. Alternatively, an anomaly in organic carbon content might reflect a brief, intense period of biological productivity linked to a rapid climatic shift. These interconnected processes underscore the complexity of the deep ocean environment and the challenges inherent in untangling the various influences. Fieldwork remains a critical component of this research. Deep-sea drilling programs, such as those conducted by the International Ocean Discovery Program, IODP, provide physical samples that are indispensable for understanding the fine-scale chemical variations in deep-sea sediments. Each sediment core, carefully extracted from the abyssal plain, is a stratigraphic record that holds clues to the Earth's past. Anomalous layers within these cores are studied in detail using a suite of analytical techniques, including X-ray fluorescence, XRF, spectroscopy, inductively coupled plasma mass spectrometry, ICP-MS, and stable isotope analysis. These methods allow scientists to determine not only the concentration of elements and compounds, but also their spatial distribution and temporal evolution. Advanced modeling efforts are also underway to better understand the processes that could generate such anomalies. Numerical simulations of sedimentation, fluid flow, and chemical reactions in the deep ocean help researchers explore various scenarios. These models incorporate factors such as sedimentation rate, bioturbation, chemical diffusion, and episodic events like underwater landslides or volcanic eruptions. By comparing the outcomes of these models with the observed data from sediment cores, scientists aim to identify the most likely mechanisms responsible for the unexplained anomalies. While progress has been made, the inherent complexity of the system means that a complete explanation remains elusive. In some cases, the anomalies have sparked debate not only over their origin, but also over their broader implications. For instance, if certain anomalies are linked to episodic remobilization events, this might indicate that the deep ocean reservoir of certain elements is more dynamic than previously thought. Such insights could have implications for our understanding of ocean circulation, nutrient cycling, and even the global carbon cycle. Conversely, if the anomalies are the result of rare geochemical reactions that occur under specific conditions, they might provide valuable information about the chemical evolution of the ocean over geological time. In either case, the study of these deep-sea chemical pollution anomalies is proving to be a key to unlocking the hidden history of our planet's largest, least explored environment. In summary, the puzzle of unexplained deep-sea chemical pollution anomalies is a compelling chapter in the story of the ocean floor. These anomalies, which manifest as unexpected spikes in the concentration of trace elements or organic compounds in remote abyssal regions, challenge our current models of sedimentation and chemical cycling. While various hypotheses have been proposed, including episodic remobilization of ancient deposits, rapid geochemical reactions triggered by environmental shifts, and localized events that temporarily alter sediment composition, none have yet provided a definitive explanation. The anomalies remain a subject of ongoing research, with interdisciplinary teams employing state-of-the-art field observations, laboratory analyses, and computational models to gradually unravel their mysteries. Each anomalous layer in a deep-sea sediment core is a record of an event, a moment when the normal flow of material was interrupted by an extraordinary process. Whether these events are linked to climatic shifts, tectonic disturbances, or other, as yet unknown, phenomena, they offer a unique window into the dynamic processes that govern the deep ocean. The continuing study of these anomalies not only enriches our understanding of Earth's history, but also highlights the inherent complexity of the natural world, a complexity that, even in its most subtle manifestations, challenges and inspires us to keep exploring. In several remote regions of the deep ocean, researchers have encountered formations on the seafloor that strikingly resemble mushrooms. These mushroom-like structures, detected primarily through high-resolution multi-beam sonar and observed in detail by ROVs, have puzzled scientists for years. Their shapes, often consisting of a broad, cap-like top connected to a narrower, stem-like base, appear both symmetric and organic, yet their origin remains unclassified, with hypotheses ranging from geological to biological processes. One prevailing theory is that these formations are the result of mineral precipitation associated with hydrothermal vent activity or cold seep processes. In many deep ocean environments, hot, mineral-rich fluids are expelled from beneath the Earth's crust. As these fluids mix with the cold, oxygenated seawater, rapid cooling and chemical reactions lead to the precipitation of carbonate minerals and metal sulfides. Under favorable conditions, these precipitates can accumulate into dome-like structures that, when eroded and modified by currents over time, acquire an appearance reminiscent of a mushroom cap rising from a narrower base. The regular, almost sculptural shape of these formations suggests that the process behind them is self-organizing, governed by factors such as fluid dynamics, temperature gradients, and the chemical composition of the vent fluids. In other regions, however, the mushroom-like formations may have a different origin. Some scientists propose that these structures are produced by sediment deformation processes. As fine sediments accumulate on the seafloor, variations in water flow and the pressure exerted by overlying layers can cause localized instability. This instability may result in the upward bulging of sediment layers, forming mounds with a characteristic cap that resembles the top of a mushroom. Over time, as the sediment continues to settle and the currents persist, the edges of the bulge can become eroded and smoothed, further enhancing the mushroom-like appearance. Such deformation may occur in areas where tectonic activity or the collapse of gas hydrate structures disrupts normal sedimentation patterns, leaving behind these enigmatic features. A third possibility is that the formations represent a hybrid of biological and geological processes. Deep-sea ecosystems are home to diverse microbial communities that thrive in the extreme conditions of the abyss. In some cases, microbes produce extracellular polymeric substances, sticky, gel-like materials that bind sediment particles together. Over long periods, this biogenic glue can promote the aggregation of mineral particles into coherent structures. The resulting formation would have characteristics of both organic growth and mineral deposition, resulting in a mushroom shape that is neither entirely biological nor purely geological. Evidence for microbial influence comes from chemical analyses of some formations, which reveal trace organic compounds and isotopic signatures that are consistent with biological activity. Yet, definitive proof remains elusive, as the observed structures do not display typical features of microbial mats, such as the irregular, patchy textures seen in shallow water environments. Field observations of these formations have been made in several ocean basins. In some parts of the Pacific, for example, extensive sonar surveys have revealed clusters of mushroom-like mounds along continental margins. In these surveys, the formations appear as distinct anomalies against the relatively uniform abyssal plain, sometimes spanning tens of meters in diameter. Detailed ROV footage has shown that some of these structures possess a smooth, rounded cap that contrasts with a more elongated base, while others display multiple layers that hint at episodic growth. The variability in shape and size suggests that local environmental conditions, such as variations in sedimentation rate, fluid flow, or the chemical composition of the water, play a significant role in determining the final form of the structure. Laboratory experiments have contributed to our understanding of how such shapes might form naturally. In high-pressure, low-temperature tanks designed to mimic deep-sea conditions, researchers have been able to reproduce mushroom-like structures by combining mineral-rich solutions with organic additives. In some experiments, the introduction of microbial cultures or synthetic polymers leads to the formation of aggregates that, after a period of settling and compaction, resemble the cap and stem morphology observed on the seafloor. These experiments demonstrate that both chemical precipitation and biogenic binding can produce structures with regular, recognizable shapes. However, the natural environment is vastly more complex than any laboratory simulation, and the precise combination of factors that results in the formation of these deep-sea mushrooms remains a matter of ongoing investigation. Geochemical analyses of sediment cores containing these formations have provided additional clues. Techniques such as X-ray diffraction, XRD, scanning electron microscopy, SEM, and laser ablation inductively coupled plasma mass spectrometry, LAICP-MS, have revealed that the formations are often rich in carbonate minerals, along with traces of sulfide compounds. In some cores, the isotopic ratios of carbon and oxygen in the carbonate layers are consistent with formation under low-temperature conditions typical of seawater, supporting the idea that these structures result from the precipitation of minerals from hydrothermal or seep fluids. In other cases, the presence of organic markers and subtle shifts in the isotopic signatures suggest that biological processes may have contributed to the formation and preservation of the structures. The spatial distribution of mushroom-like formations also provides important context. They are not randomly scattered across the seafloor. Instead, they often occur in areas where geological or chemical gradients are pronounced. For instance, near active vent fields, the continuous supply of mineral-rich fluids may lead to the frequent formation of such structures. Similarly, in regions where sedimentation rates are unusually high or where fluid flow is concentrated along fault lines, the conditions may favor the repeated development of these anomalies. Mapping these distributions using modern geophysical techniques has helped scientists identify patterns that could be linked to underlying processes, such as localized episodes of fluid discharge or variations in sediment composition over time. There is also an intriguing possibility that some of these formations record past environmental events. If a particular formation can be dated using radiometric techniques or by correlating it with known climatic events, it might serve as a marker of a specific period in Earth's history. For example, an anomalous layer that aligns with a known volcanic eruption or a rapid climatic shift could indicate that the mushroom-like structure formed as a direct response to that event. Such findings would not only help explain the origin of the formation, but also contribute to our understanding of the deep-sea sedimentary record as a whole. The debate over the origin of these formations is far from settled. While many studies lean toward a natural geochemical explanation, the possibility of a biological influence or a hybrid mechanism remains open. Some researchers advocate for further in situ observations using next-generation AUVs equipped with more sensitive imaging and sampling tools. These vehicles, capable of operating for extended periods in the abyss, could provide continuous, high-resolution data on the formation processes. Over time, the accumulation of such data may allow scientists to build more refined models that accurately capture the interplay between chemical, physical, and biological factors in the deep ocean. Interdisciplinary collaboration is crucial to advancing our understanding. Geologists, oceanographers, chemists, and biologists are increasingly working together to integrate data from field observations, laboratory experiments, and computational models. By pooling expertise and employing a range of analytical techniques, these teams aim to untangle the complex processes that give rise to the mushroom-like formations. The synthesis of these efforts is gradually revealing a picture in which the formations are the product of natural self-organization, a result of the ocean's dynamic processes operating under extreme conditions. In summary, enigmatic mushroom-like seafloor formations represent one of the deep ocean's many intriguing mysteries. Whether formed by the precipitation of minerals from hydrothermal fluids, by sediment deformation processes, or by the subtle interplay between biological and geological forces, these structures defy simple classification. Their distinctive cap and stem shapes, revealed through advanced sonar mapping and ROV exploration, provide a tantalizing glimpse into the processes that shape the seafloor over geological timescales. Although many questions remain, ranging from the precise environmental conditions that favor their formation to the mechanisms that sustain their unique shapes, the ongoing research continues to advance our understanding of these fascinating features. Every discovery in this realm deepens our appreciation for the complexity and dynamism of the deep ocean. The mushroom-like formations are not anomalies in the sense of being inexplicable. Rather, they are the natural outcome of processes that, under the right conditions, produce regular, self-organizing structures in an environment where change occurs at a glacial pace. Their study is a window into the Earth's past and a key to understanding how the interplay of chemistry, biology, and physics can yield forms of unexpected beauty and complexity. As researchers continue to probe these formations with ever more sophisticated technology, the hope is that their origins will gradually come into clearer focus, shedding light on one of the ocean's most persistent puzzles. These structures, silent and enduring, remind us that even in the remote, inaccessible depths of the ocean, nature continuously crafts intricate records of its activity. Each formation is a chapter in the long and ongoing story of Earth's dynamic processes, a story that challenges our perceptions and invites us to explore further. The mystery of mushroom-like seafloor formations endures as a vivid illustration of the natural world's ability to organize and transform over millions of years, leaving behind a legacy that is as scientifically significant as it is visually captivating. Deep-sea mounds have long been an enigma in the vast, silent depths of our oceans. In many parts of the seafloor, particularly along continental margins and near cold seep zones, scientists have discovered clusters of smooth, dome-shaped elevations rising gently from the sediment. These formations, often appearing as circular or elliptical mounds, vary in size from modest bumps only a few meters across to larger structures that stretch over tens of meters. Their precise origin is not yet fully understood, and that very mystery invites us to delve into the subtle interplay of geological, chemical, and sometimes even biological processes that give rise to them. One of the most widely accepted ideas is that many of these mounds result from the process of anaerobic oxidation of methane, an intriguing chemical reaction that occurs in the absence of oxygen. Deep beneath the seafloor, methane is generated by the decay of organic matter, often in areas where the sediments are rich with biological remnants. In regions where the upward migration of methane intersects with sulfate-rich seawater, specialized communities of bacteria come into play. These microorganisms use methane as an energy source in a reaction with sulfate, producing bicarbonate ions as a byproduct. Over long periods, the bicarbonate ions combine with calcium present in the water to precipitate calcium carbonate. Layer upon layer of this precipitate accumulates on the seafloor, gradually forming mounds that can be detected as raised structures in sonar maps. This slow, natural process of carbonate precipitation explains not only the formation of many deep-sea mounds, but also their relatively uniform, rounded shapes. As the chemical reaction continues over thousands or even millions of years, the resulting carbonate deposits tend to self-organize into domed forms, guided by factors such as the local water currents, pressure, and the inherent properties of the minerals themselves. The final product is a mound that appears almost sculpted by the invisible hand of nature, a quiet, persistent structure that stands out against the otherwise flat, sediment-covered abyss. In some cases, these mounds are associated with cold seep ecosystems. Cold seeps are areas where hydrocarbons and other fluids escape from the subsurface into the ocean, providing a rich source of energy for specialized organisms. Along with the carbonate mounds, vibrant communities of mussels, clams, tube worms, and various chemosynthetic bacteria flourish, forming an oasis of life in the otherwise sparse deep-sea environment. The mounds serve as both physical platforms and chemical reservoirs, supporting life forms that have adapted to extreme conditions. The presence of these biological communities can sometimes modify the formation process further. For instance, the decay of organic matter and the activity of benthic organisms might influence the local chemistry, subtly altering the rate or composition of carbonate precipitation. Yet not all deep-sea mounds are neatly explained by the methane oxidation pathway. Some mounds appear in areas where hydrothermal venting is minimal, or where there is no obvious source of methane in the sediment. In these regions, alternative processes are considered. One possibility is that some mounds form as a result of sediment deformation driven by tectonic forces. The seafloor is not a static landscape. It is constantly being reshaped by the movement of tectonic plates, sediment slumping, and even the slow, persistent flow of ocean currents. In some cases, the stress exerted on soft sediments can cause them to bulge upward, forming mounds. These features, often referred to as pockmarks or mud volcanoes when associated with fluid expulsion, can appear strikingly similar to carbonate mounds. However, detailed geochemical analyses usually reveal a different composition, suggesting that the driving forces behind their formation are mechanical rather than chemical. Another intriguing hypothesis is that some deep-sea mounds could be related to the dissociation of gas hydrates. Gas hydrates are crystalline structures that trap methane within cages of water molecules, and they are stable only under the high-pressure, low-temperature conditions found on the continental slopes. If conditions change, perhaps due to a warming of the ocean bottom or a shift in pressure, the hydrates can destabilize, releasing methane. The sudden release of methane can lead to localized fluidization of the sediment and subsequent mound formation as the sediment is reworked and deposited in a new configuration. Although this process is still under active investigation, it provides a plausible mechanism for mound formation in regions where methane seeps are present, but where the anaerobic oxidation pathway does not fully explain the observed structures. Deep-sea mounds are also studied using advanced remote sensing technologies. Multi-beam sonar systems mounted on research vessels generate detailed maps of the seafloor, revealing the topography and distribution of these mysterious mounds over vast areas. High-resolution images collected by remotely operated vehicles, ROVs, allow scientists to closely examine the surface textures and morphologies of individual mounds. In some surveys, the mounds appear to be remarkably regular in shape, with smooth, rounded contours that suggest a long history of gradual deposition. In other cases, the mounds display more irregular features, ridges, depressions, or even channels that hint at episodic events or variations in the formation processes. One fascinating discovery is that the spatial distribution of deep-sea mounds sometimes follows a pattern that hints at underlying geological controls. For instance, on some continental margins, mounds are aligned along faults or fractures, suggesting that tectonic activity might be providing pathways for fluid migration. In other regions, clusters of mounds occur in areas with anomalously high heat flow, indicating that residual magmatic activity or deeper-seated fluid circulation could be influencing their formation. Such patterns provide valuable clues that help scientists build models of fluid dynamics and sedimentation in the deep ocean. By comparing the observed mound fields with predictions from these models, researchers are slowly piecing together a more comprehensive understanding of how and why these structures form. The composition of the mounds is studied through a variety of techniques. Rock and sediment samples retrieved by ROVs are analyzed using X-ray diffraction, XRD, and scanning electron microscopy, SEM. These methods allow scientists to determine the mineralogical makeup of the mounds, often revealing high concentrations of carbonate minerals such as calcite or aragonite. In cases where mounds are associated with cold seeps, the samples may also contain traces of sulfide minerals, which form in the presence of hydrogen sulfide produced during methane oxidation. Isotopic analysis further helps to constrain the age and formation history of the mounds. The ratios of carbon and oxygen isotopes in carbonate minerals can indicate the temperature and chemistry of the fluid from which they precipitated. Such data are essential for differentiating between mounds formed by methane oxidation, those resulting from gas hydrate dissociation, and those that are purely tectonic in origin. While the formation of deep-sea mounds is now largely attributed to natural processes, the exact details remain a subject of active research. The relative contributions of biogeochemical versus mechanical processes continue to be debated. For example, while the anaerobic oxidation of methane clearly plays a major role in many mound systems, there are instances where the chemical signatures do not match expectations from this process alone. In such cases, additional factors, such as variations in the supply of methane, changes in the local sediment composition, or episodic geological events, might have contributed to the mound's development. The temporal evolution of these mounds is another area of keen interest. Some mounds appear to have been growing steadily for hundreds of thousands of years, while others show signs of rapid formation over much shorter timescales. Understanding these growth patterns is essential for reconstructing the environmental history of the deep ocean and for linking mound formation to broader geodynamic processes, such as sea level fluctuations and shifts in ocean circulation. There is also the role of post-depositional processes to consider. Once a mound is formed, it does not remain static. Over time, biological, chemical, and physical weathering processes can alter its shape and composition. For instance, as ocean currents redistribute fine sediments, the mounds can become partially buried, or their surfaces may be smoothed even further. In some cases, microbial activity can lead to the dissolution of carbonate minerals, gradually eroding the mound from the outside in. Such processes add yet another layer of complexity, making it challenging to determine the original formation mechanism from the current morphology of the mound. Some deep-sea mounds have also been linked to economic interests. In certain regions, carbonate mounds associated with cold seeps are known to host rich deposits of precious minerals or hydrocarbons. These mounds can serve as natural traps for oil and gas, and understanding their formation is critical for assessing the potential of deep-sea resource exploration. While economic exploitation of such resources is controversial and subject to strict environmental regulations, the scientific study of these mounds provides valuable insights into the natural history of the ocean floor. In recent years, international collaborations have expanded the research on deep-sea mounds. Teams from universities, research institutes, and government agencies have joined forces to conduct large-scale mapping projects in areas known for their venting activity and tectonic complexity. These projects, often funded by a combination of public and private resources, aim to produce detailed three-dimensional maps of the seafloor. By correlating acoustic data with ground truth obtained from sediment cores and rock samples, scientists are gradually refining their models of mound formation. Such collaborative efforts are crucial because they bring together diverse expertise from fields such as geophysics, chemistry, biology, and ocean engineering. One particularly promising avenue of research involves the use of autonomous underwater vehicles, AUVs. These vehicles are capable of operating for extended periods without human intervention, gathering high-resolution images and sensor data from regions that are otherwise inaccessible. AUVs equipped with advanced sonar systems have been able to detect subtle variations in seafloor topography that reveal the presence of mounds hidden beneath layers of sediment. Over time, the accumulation of data from multiple AUV missions is expected to reveal patterns in mound distribution, providing further clues about their underlying formation processes. With each new survey, the picture becomes a little clearer, and the interplay of natural forces that creates these enigmatic structures comes into sharper focus. Although the mystery of deep-sea mounds might seem remote and abstract, its implications are far-reaching. These structures are not only windows into the geological processes that shape our planet, but also serve as archives of Earth's environmental history. The chemical signatures locked within the carbonate layers can tell us about past ocean temperatures, the intensity of methane emissions, and even shifts in global sea level. In this sense, each mound is like a natural time capsule, preserving a record of events that occurred over millennia. As researchers continue to decode these records, they may uncover insights that have relevance not only for our understanding of Earth's past, but also for predictions about future climate and oceanographic trends. Despite decades of study, deep-sea mounds remain one of the ocean's most persistent mysteries. The very fact that these formations exist, so uniformly shaped, so widespread, and yet so difficult to explain, underscores how much there still is to learn about the processes occurring in the dark, pressurized depths of the ocean. In this endless twilight, where light scarcely penetrates and the pressure is immense, nature performs feats of self-organization that challenge our expectations and inspire wonder. The mystery of deep-sea mounds invites us to reflect on the beauty and complexity of natural processes. As you let your mind wander over the imagery of vast, silent seafloors punctuated by these mysterious domes, consider the interplay of factors that bring them into being: the slow, inexorable forces of chemical precipitation, the turbulent interplay of vent fluids and cold seawater, the gentle but persistent action of ocean currents, and the subtle, often overlooked contributions of biological activity. Together, these elements conspire to create mounds that are at once simple in their form and profoundly complex in their origin. The study of these deep-sea mounds is a journey into one of Earth's final frontiers, a realm where the laws of physics and chemistry interact in ways that are still not fully understood. Every new observation, every sample analyzed, adds another piece to a puzzle that has been assembling for eons. And while many details remain shrouded in mystery, the ongoing research is steadily illuminating the processes behind these natural wonders. For scientists, every mound is a quiet challenge, a call to look closer, think deeper, and push the boundaries of our understanding of the planet's most remote environments. In the calm, methodical pace of deep-sea exploration, there is a lesson in patience and curiosity. The deep ocean does not yield its secrets easily. It requires careful observation, rigorous analysis, and often a willingness to embrace uncertainty. As researchers continue to refine their techniques and develop new technologies for exploring the seafloor, the mystery of these mounds is slowly coming into focus, a testament to the power of nature to create order out of chaos, even in the most extreme conditions. These deep-sea mounds, silently rising from the sediment like relics of a bygone era, are a reminder of the enduring complexity of our planet. They stand as monuments to the subtle, persistent processes that have shaped Earth's surface over millions of years. And although their full story may not be completely unraveled for some time, each discovery brings us one step closer to understanding the delicate balance of forces that govern our world. In this quiet exploration of deep-sea mounds, there is no need for sensational theories or dramatic conclusions. The evidence, gathered with patience and precision, points to natural processes operating under extreme conditions. The mystery remains, not as a puzzle to be solved with haste, but as an invitation to appreciate the intricate beauty of our planet's hidden realms. A beauty that is both scientifically fascinating and profoundly soothing. As you listen, let your thoughts settle like fine sediment on the seafloor, and allow the gentle narrative of natural wonder to carry you deeper into a state of calm reflection. The mystery of deep-sea mounds is a story of gradual transformation, a narrative written over countless years by forces that are as relentless as they are gentle. And in that story, every new piece of evidence is like a soft echo in the deep, inviting us to listen a little more, think a little deeper, and rest a little easier in the vast, mysterious silence of the ocean floor.